Hi everyone. Okay, so today we will start pumping lemma, and this pumping lemma, you just understand step by step everything that I tell you. Every small point is very important, so focus. Okay, pay attention. Okay, because this pumping lemma is not a easy thing, but we will try to make it easy. Okay, and we will take a lot of examples. So let's check it out. So first, what is this pumping lemma? Okay, this let's study. Just wait. Okay, yeah. So let's start pumping lemma. So we will make some observations about DFA, and from those observations we will find out the proof of pumping lemma. Okay, don't worry, pumping lemma is just a property of regular languages. Okay, so let's check it out. First, let me give you a DFA. Okay, consider this DFA. Can anyone tell me which language this DFA is accepting? Consider this DFA, and what is the language of this DFA? Can you notice in this DFA? You can notice okay. So if you see the language, so what you can do, either you can take A or you can take regular expression. Let's write the regular expression. So from initial state, you are here. From initial state, either you can take this A or you can take B A star A, B A star B. Okay, and after that anything can come. After that sigma star, correct? Okay, so this is the regular expression. Very good. So this is the language. Now this is your initial state P, this is your Q, this is your R. Now my let's see. Okay, let's take some strings. Okay, so take this string W equal to A. Now from on this string, how many states this DFA, how many states this DFA will visit? So you can notice this is your string. So DFA will start in the initial state. Okay, so in the initial state, if you see the symbol A, where will you go? You will go to Q. So can you notice that if your string has length 1, your string has length 1, so in that case DFA is going through 2 states. Let's take this string A. Tell me how many states. Okay, in the sequence of states, basically this DFA will go through a sequence of states, correct? This DFA will go through a sequence of states. Okay, and how many states are there in that sequence? So let's check it out. So this is your string. Initially the DFA is in P state P, initial state. In the initial state, if you read symbol A, if you consume this symbol A, you will go to Q. In this state Q, if you consume the symbol A, you will go to Q. In this state, if you consume the symbol A, then you will go to this state. You can notice that DFA is going through a sequence of states. Okay, and in this sequence, how many states we have? Total 4 states we have. So length of W is 3. So in this sequence of states, we have 4 states. So basically, very simple thing. If you have any DFA that you have, okay, in this DFA, for this string, if you have a string W whose length, let's assume string length is equal to n. Okay, in that case, okay, so for this string, let's assume this is your string A1, A2, A3, and so on, AN. This is your string. Okay, now tell me, this DFA will start where? This DFA will start in the initial state. It will start in the initial state. Okay, so this DFA and you have this string has length n, the length of this string is n. So how many states? Okay, so you can notice very simple that this DFA will go through a sequence of states. In the initial state, if you read this symbol, then it will go to some state. Okay, in this state, if you read this symbol, it will go to some state, it will go to some state, and so on. So finally, how many states in this sequence? How many states we have? So in this sequence, we have total n plus 1 states. Correct? So whatever string you take, okay, this is the simple point. Whatever string you take in a DFA, okay, so for any string of length n, the DFA will go through DFA will go through a sequence of n plus 1 states. Okay, so this point we can say. Okay, so this is a property of DFA that we can say that, okay, any DFA, you have a DFA, okay, on string, on any string, any DFA on any string of length n goes through a sequence of states, and for string w of length, this, okay, number of states in this sequence. What is the number of states in this sequence? In this sequence is length of string plus 1. Correct? Okay. No, any string, you can take any string. The DFA will go through total n plus 1 states. So for example, you can check it out. Okay, this DFA on string B. So how many states this DFA will go through? This DFA on string B, you can notice this DFA will start here. This DFA will definitely start in the initial state, and if you read this symbol B, then it will go to state R. So you can notice for this string, the DFA is going through 2 states. Okay, so you can notice. Similarly, for empty string, the DFA is going through, okay, only 1 state, because you can notice initially your DFA is in this state. Initially your DFA is in this state, and string is entered. Yes or no? Can you notice? I told you when we were studying DFA, I told you at that time, what did I tell you? I tell you that input tape looks like this. Yes or no? Input tape looks like this. Okay, so okay, you can very easily notice that your input tape looks like this. So once you start, you are ending. Yes or no? As soon as you start, you are ending. Correct or not? So basically you can see as soon as, okay, for empty string, this I told you many times that for empty string, okay, input tape looks like this. Okay, so as soon as you start, you are ending. As soon as you start, you are ending. Okay, and as soon as you start, you end. Okay, so you can notice that for this string, the input tape will look like this. So as soon as you start, you are ending. So for this string, how many? Okay, again, for this string also you can notice, for this string we are going through only a sequence of 1 state. Correct? Shuru hote hi khatam. Okay, correct or not? So very simple. Now, okay, so for this string, you tell me. Yeah, you can notice this is the sequence. I am talking about sequence, Sandeep. I am talking about sequence. And I told you in discrete mathematics, okay, this is a sequence. Yes or no? This sequence, this is a sequence, and these 2 sequences are different. This I told you in discrete mathematics. Sequence, this is a ordered list, basically. Ordered list. Okay, so I'm talking about sequence here. So you can notice for this string, the DFA is going through this sequence, P, Q, Q, Q. Okay, and for this string, DFA is going through this sequence. For this string, DFA is going through this sequence. For this string, DFA is going through this sequence. So for any string of length n, if you have any string of length n, then DFA is going through okay, then DFA is going through n+1 states, correct? So this is the point, very simple point, very simple observation about DFA, correct or not? Okay, let's take this observation. Let's assume, let's take this DFA. Is this dead state or not? Do you remember this type of state we call dead state, correct? Okay, so let's call it P, let's call it Q. Now tell me, for this string, DFA will go through a sequence of states, yes or no? When DFA is running, this is your DFA, and when you run DFA, okay, on W, then you can notice that DFA will go through a sequence of states, A, B, 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 A. Okay, so now you can notice DFA will start from P, then it will go to Q, then it will go to Q, 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 Q. So you can notice for this string, this is your input tape, this is your input tape. Okay, and for this string, I can say that your DFA is going through this sequence of states. In this sequence, how many states we have? So total we have, okay, this string has length, so this string has a length 5. Okay, so in this sequence we have total 6 states, correct? So in this sequence we have total 6 states in this sequence, correct? Okay, so this is the point, this is the observation I want you to make. Okay, now let's make another observation. Okay, now consider this DFA. Let me give you a DFA. A, B, okay, and then A. Now let's take this DFA, correct? Now one more observation we are going to make, and what is that? That let's assume that you take this string, any string you take. For example, consider this string. This is state P, this is state Q, this is state R. So consider this string. Okay. Now, okay, let's consider. Let's make this non-final and let's make this final. Okay, let's do this. Now let's consider this string. Okay, so this is your final state. Now tell me, what will be the sequence of states the DFA will go through? DFA will start here, DFA will go to Q, and DFA again will go to Q. Can you notice one thing? Okay, can you notice one thing? That now this string is accepted, right? Because this is final state, so this Q is final state, so this string is accepted. But can you notice one thing? That, okay, so this repetition of state Q, can you notice this repetition of state Q? So tell me, okay, this Q on this symbol B, this is repetition. Okay, this thing is repetition, yes or no? This, if again another symbol B comes, okay, because of this behavior, if another symbol B comes, then what will happen? Then again you will go to Q, because this behavior, okay, just notice this behavior, because your DFA is deterministic. DFA is deterministic, so this behavior will always happen. If another B comes, then again you will go to Q. If another B comes, again you will go to Q. So we started from this. See, this string we started. Okay, you can notice, you can observe one thing, that we started with this string. This is the string we started. But for this string, what we found that this state is repeating. This state is repeating. Okay, because, okay, you can notice this state is repeating. So this part, okay, between this state and between this state, this part, I can repeat any number of times, correct or not? This simple observation, I can repeat this any number of times, because your DFA is deterministic. So it will always happen that you will have this type of situation. So I can repeat this any number of times, correct? This part, okay, this part I can repeat any number of times. I can put this, I can put this. Okay, you can notice I can put this. For all the sequences, I will go from P to Q, yes or no? I will go from P to Q, correct or not? I will go from P to Q for all these. Can I repeat it 0 times? Can I repeat this? Can I repeat this 0 times? This 0 times means only this much, only this much. I am repeating this 0 times. Yes, I can do that, because from P to Q. Okay, Again, you can notice I can repeat this 0 times also. So this small observation, okay, we are making small observations we are making, and I will tell you why we are making these observations. Don't worry. But let's make another observation. Okay, so let's take another question, and in this question, let's try to create another observation. Okay, so this is your state P, and let's assume so this, consider this. Okay, P, this state is P, this state is Q, this state is R, this state is S, and let's assume this is your, okay, is this DFA? Can you check it out? Is this DFA? Is it DFA? Yes, of course, this is DFA, right? Now, okay, so take this string. Now, okay, consider this string A, okay, A, then you have A, then you have, yes, consider this A. Tell me, for this string, will we, in the sequence of states, will we see a repetition? For this string, in the sequence of states, will we see repetition? We will not see, because P, when, okay, P on A, that will go to Q, Q on A, that will go to R. So you can notice, for this string on sequence of states, we are not seeing any repetition. Now let's check this string. Let's check it out, this string. Tell me, for this string, in the sequence of states, will we see any repetition? Yes, now we will see repetition from P to Q, and from Q on A to R, and from R on A to R. Okay. Now, so you can notice that for this string, we will see repetition. And tell me, for this string, A, B. Okay, let us check it out. This string you take. So tell me, your DFA will start in state P, then it will go to Q, then it will go to R, then it will again go to R, and then it will go to S. Correct or not? For this string, consider this string. Now you can notice that if you have this string, then your DFA is going through this sequence, and there is a repetition. There is a repetition. Okay, so repetition is happening for this string, correct? For this substring. For this substring, this is your substring. For this substring, repetition is happening. Can you notice? Repetition is happening. So it means, can I say that I can repeat this? Because no problem. Okay, because you can notice, if I put another, just think about it and tell me, if I put another A, then where I will go? Because you can notice, okay, because you can notice that if I put another A, again I will go to R. Okay, you can notice, very simple. Again I will go to R. So you can notice this is substring. This substring, okay, this we have repeated. Can you notice? This substring we have repeated. So we have repeated 2 times. Can I say this substring I have repeated 2 times? Can you repeat 3 times? Can you repeat 3 times? A. Yes, this substring I can repeat 3 times also. Because if I repeat again, I will go to R. If I repeat again, I will go to R. Okay, then B, then S. Now you can notice this substring I have repeated 3 times. Okay, and you can notice in all these repetition, I'm starting from P, I'm going to S. I'm starting from P, I'm going to S. I'm starting from P, I'm going to S. Okay, so this repetition does not change where I'm going. Yes or no? Can you notice this repetition does not change where I am going? From initial state, I'm going to S. From initial state, I'm going to S. From initial state, I'm going to S. Can I repeat this 0 times? Let's repeat this 0 times. A. Repeat this 0 times means remove this. Means remove this. Then you can notice, if I repeat this 0 times means just remove this. Just remove this. So I will go to P, Q, R, S. Again, you can notice, no problem. From P, I am going to S. Correct or not? Is this point clear to everyone? Okay. So let me ask you one more question. If you have a DFA of n states, what can you guarantee? Like you have a DFA, let's assume you have a DFA and it has n states. And for this DFA, what can you guarantee if your string, if I give you a string of length, if I give you a string of length n, if you have a string of length n and your DFA has n states, okay, so your string has length n, it's like this: a1, a2, a3, an. This is your string and your DFA has n states. Now tell me, what can you guarantee? I can guarantee that in this sequence at least one state will repeat. This I can guarantee, correct? Why? I can guarantee, we can guarantee that in this sequence, in this state sequence, I can say, okay, in this state sequence, at least one state will repeat. This I can guarantee, at least one state will repeat. Why? This state, at least one state will repeat, because in this sequence you will have n plus 1 states. In this sequence we have n plus 1 states in this sequence, okay, and total we only have n states. So in this sequence we have n plus 1 states and total we have n states. So I can guarantee that at least one state must repeat. Yes or no? By pigeonhole principle, we can guarantee that at least one state must repeat. Correct? Okay. So this is the simple point. Now, can you guarantee? So can you guarantee this? The same guarantee can you give for this? If okay, can you give the same guarantee if your string has length n minus 1? Can you give this guarantee? Can you guarantee? Can you guarantee? Can you guarantee? No, you cannot guarantee. Why? Because now this sequence has n states. Okay, so now this sequence has n states. Now we cannot guarantee. We cannot guarantee that in this sequence at least one state will repeat. Maybe no state is repeating. Okay, maybe no state is repeating because we have n states and in this sequence we have n states. So we cannot guarantee. Correct? Okay. So you can notice, okay, for example, you consider this example, you consider a comma b, and then you go to some final state and then a comma b. For this DFA, you can notice that you have total how many states? In this DFA, you have total 3 states. Okay. Do we have any string of length less than 3 where state will repeat? Do we have any string of length less than 3? Do we have for which state will repeat? No. Okay, we don't have, right? For any string, the state will never repeat. The state will never repeat. Can you notice? The state will never repeat. For this DFA, you can notice. For this DFA, you can notice that if you take any string of length less than 3, then you can notice state is not repeating. But tell me, if I take any string of length 3, the state will repeat or not? At least one state will repeat. If you take any string of length greater than or equal to 3, then definitely state will repeat because you can notice that, okay, you can notice that definitely state will repeat. Correct? Okay. So let's take another example. Can I guarantee that for string less than n, state will never repeat? Can I guarantee this? You have a DFA, D, and let's assume total n states you have. Then, okay, for W whose length is less than n, can we say state will not repeat? Can we say state will not repeat in the state sequence? Some DFA you have, okay, let's assume you have some DFA you have, state will not repeat in the state sequence. The answer is no. We cannot give any such guarantee. We cannot give. For example, consider this DFA. Let me give you this DFA. Okay, consider this DFA. You can notice that if you take this string, the state will repeat, yes or no? If you take this string, then you can very easily you can notice the state will repeat. If you take this string, then again you can notice the state will repeat. So we cannot give any guarantee if your string has length. If your string has length less than n, we cannot say anything. State may repeat, state may not repeat, we cannot say anything. But if your string has length greater than n, then we can guarantee, yes or no. So this is the fundamental point behind pumping lemma. Okay, so this is the final point I want to say. Basically, you have any DFA, okay, any DFA M you have, in which you have total, let's assume total n states you have. Now, okay, if your string, if you take any string whose length is greater than or equal to n, you can guarantee that at least one state will repeat. Okay, we can guarantee that in the state sequence at least one state will repeat. Okay, so this we can guarantee. This thing we can guarantee. If your string has length less than n, then state may or may not repeat. We cannot say anything. State may or may not repeat. So we cannot say anything. Clear? Okay. Now another simple point I want to say, if state is repeating, let's assume, so you have a string, and for this string you have, okay, some string a1, a2, and let's assume some a3, a4, a5, and now let's assume that some state is repeating and like this: p, q, r, q, okay, s, t. Now let's assume this is happening in, okay, so this is your string, and for this string this is the state sequence in a DFA. We are talking about some DFA. Now tell me, okay, you can notice this is repetition, yes or no? So you can notice, okay, let's call this part, for this part state is repeating, correct or not? Let's call this part y. Just let's call this part y. Okay, now tell me, if I remove this part y, still I will go from p to t, yes or no? If I remove this part y, just remove, let's remove a1, a4, a5. So tell me, you are starting in p, on this a1 I will go to q. Okay, now q on a4, where I am going, tell me. Q on a4, you can notice Q on a4 I am going to s. Q on a4, you can notice Q on a4, I am going to s, and s on a5 I am going to t. Correct? So I can report, okay, so let's call this part x, and let's call this part z. Okay, so you can notice here, what is this? This is your xz, yes or no? This is xz, correct or not? This string is xz, correct? This string is xz, because this part I am removing. This substring I have removed, correct? Can I repeat this substring? For example, a1, a2, a3, a2, a3, okay, then a4, a5. Now tell me, DFA is in P. On A1, where I am going? P on A1, I am going to Q. Q on A2, I am going to R. R on A3, I am going to Q. Q on A2, I am going to R. R on A3, I am going to Q. You can notice R on A3, I am going to Q. Q on A2, I am going to R. Now Q on A4, I am going to S. S on A5, I am going to T. Okay, so tell me, what is this string? This is x, y square z. Yes or no? This is x, y, y, z, correct? X, y, y, z. Can I repeat this again? Tell me. Yes, I can repeat this again. So you can notice that for this one thing, you can notice that your DFA, if you notice, your DFA on W, on this string, your DFA is going to state T. Okay, from here you started. Okay, and you can notice this was happening. This was happening. What was happening? QQ. This was happening, correct? This thing was happening. So this was the initial situation, and this was your W. Okay, if you repeat now, you can repeat this 0 times. So now you have some other string. You have XZ. Okay, P Q T. No problem. But the point is, again, you are going from P to T on this XZ also. Similarly, I can say that on this X, Y, Y, Z also you will go to from P to T. On this string also X, Y, 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 Z, again you will go from P to T. Correct? This will happen. Yes or no? Because your DFA is deterministic. If this observation is clear, then this pumping lemma is over. Okay. So this is your, let's assume this is your DFA, and run this DFA on this string. Tell me where you will go. This DFA you run on 0, 1, 1, 0, 1, 1, 1. So this will be the state sequence. Your state sequence will be this, correct? Now you can notice that, okay, so 0, 1, 1, 0, 1, 1, 1. Okay, now you run this DFA. Tell me, okay, just by looking at it, what is the length of this string? Just tell me this. Length is 7. Yes or no? Length is 7. The length is 7. And how many states in the DFA? In this DFA, how many states we have? You can notice we have total 6 states. So can I guarantee some repetition will happen? In DFA, number of states, you can notice number of states is 6. Can I guarantee that in the state sequence, some repetition will definitely happen? I can guarantee. Because in this state sequence, this is your state sequence. In this state sequence, we will have how many states? Total 8 states we will have. Yes or no? Total 8 states we have in this state sequence. And in your DFA, you only have 6 states. But in DFA, 6 states you have. So definitely some repetition will definitely happen. Okay, let's check. So from initial state Q0, you are in the initial state Q0. Where are you going? On the initial state Q0. Then you are going to Q1, Q2, Q3, Q1, Q2, Q3, and then Q1, Q2, Q3, then Q1, Q2, Q3, and Q4. So you know at least one repetition will definitely happen, and you can notice at least one repetition is happening. Correct or not? Can you notice here repetition is happening? Yes or no? At least one repetition will definitely happen. At least one repetition. So this repetition is happening. Correct? Yes or no? Now let's call this. Let's call this part. Okay. So before this repetition, let's call this X. This part, let's call it X. Okay. And let's call this part between the repetition, let's call this Y. And after the repetition, let's call this Z. Okay, clear? So what I'm doing, is it clear to everyone? So before the repetition, from the initial state, before the repetition is happening here. Okay, 1, 1, 0. Let's call it Y. After the repetition, let's call it Z. And okay, before the repetition, let's call it X. Correct? So this is what I am doing. Okay. So you can notice Q0, and here I am Q1, and here I am Q1, and here I am Q4. Now let me ask you one question, that on this, if I remove this, okay, this repetition is happening. If I remove this part, let's 0, 1, 1, 1. Where this DFA will go? Tell me. 0, 1, 1, 1. 0, 1, 1, 1. So Q0 to Q1, then Q2, then Q3, and then Q4. Q0, Q1, Q2, Q3, Q4. Yes or no? Q0, Q1, Q2, Q3, Q4. Correct? Now again, you can notice very simply, if I remove this part, if this part I remove, then you can notice, you can very easily notice, if I remove this part, I'm okay, initially I'm in Q0. After reading this X, I am going to Q1. Now, from Q1 on reading Z, from Q1 on reading Z, I am going to Q4. Yes or no? This is happening. Yes or no? This is happening because from Q1 on reading Z, I am going to Q4. That's it. Okay. So this is what happening. So this, can I say basically what I have done here? Here I have done x y power 0 z. Yes or no? On x y, okay, you are going from Q0 to Q4. On this also. So this is what happening. On x y z, you are going from Q0 to Q4. On xz also you will go from Q0 to Q4. If I repeat this part, then again you will go from Q0 to Q4. Okay, if I repeat this part 100 times, then also you will go from Q0 to Q4. Correct? Correct or not? This will happen or not? Yes? Right? Is it clear? So is this point clear? You can repeat any number of times. That's it. Okay. So this is your pigeonhole prints. This is your pumping lemma. Now let me tell you, okay, what is pumping lemma? Yes, Namrata, right now just example I have taken. Don't worry. I have just taken example. Now let's take another example. Let me take just, okay, consider this example. Now consider this string PQ B. Consider this string. So tell me, this is your string. Now tell me, for this string, this is your string. For this string, what will be state sequence? Give me state sequence for this string. Give me the state sequence for this string. You will start in P. On B, you will go to P. On A, you will go to Q. Can you see there is a repetition? Can you see there is a repetition? Okay, there is this repetition. So before this repetition, okay, tell me what is your X, what is your Y, what is your Z? This is your repetition. So this is your Y. I told you this is your Y. Before this repetition, this is your X. Can you see this is your X? Yes or no? And this is your Z. Yes or no? Tell me yes or no. This is what I'm saying. Basically, your, okay, you have this type of situation. You have this type of situation. If you have this type of situation, then okay, this repetition is happening. This we are calling between the repetition. This is your Y. Before this repetition, this is your X, and after this repetition, this is your Z. So you can notice this is your X is epsilon, Y is B, and Z is A. So again, you can very easily notice I can repeat this Y any number of times. Correct or not? This repetition I can again repeat any number of times. I can remove Y. If I remove Y, I will get this. And you can notice again I am going from P to Q. No problem. You can notice on this string, very simple point you can notice. On this string, I am going from P to Q. Okay. And if I remove this Y, if I remove this part Y, now again I am going from P to Q. If I repeat this part Y, this is your part Y. If I repeat this part Y 2 times, then also I am going from P to Q. If I repeat this part Y any number of times, then again I am going from P to Q. Yes or no? Tell me. Is it clear to everyone? Is this clear? So can you notice this X can be empty? Yes or no? X can be empty. This part means this part before repetition. This part before repetition, this can be empty. So this point you can notice here. So you can notice very simple point you can observe. The X part can be empty. Okay. Now for same DFA, if I give you a string B, same DFA for string B, what will happen? So let me say same DFA you have. So you have this same DFA. For string B, what will happen? What will be the sequence? This is your string. And what will be the state sequence? its state sequence will be what? This is P, this is Q. So state sequence will be from P to P. Okay, so again you can notice there is a repetition. Again there is a repetition. So tell me, what is your X, what is your Y, what is your Z? What is your, this is repetition. This is repetition of state. What is your X? Your X is epsilon and your Z is also epsilon. Yes or no? Your X is epsilon, your Z is also epsilon. Correct? So that's the simple point. Now you can very easily notice that, okay, this is your Y. This part is your Y. You can repeat this any number of times. Again, okay, if I repeat this 0 times, can I guarantee I will go from P to P? If I repeat this Y 0 times, if I repeat this Y 0 times, then can I guarantee I will go from P to P? Yes. Yes, I will go from P to P basically. Correct? On empty string, you can say that I will go, okay, because you have empty string. So again, no problem, because on empty string, I am going from P to P. No problem. Okay. So I can write like this, but don't, okay, this is not the sequence actually. I should say only this much. Okay, P. Now tell me for this, if I repeat this, if I repeat this 2 times, again I will go from P to P. Correct? If I repeat this 100 times, again I will go from P to P. Clear? So X, Z, they can be empty. Okay. And this is your Y. So is this clear to everyone? Why can Y be empty? Can Y be empty? Can Y be empty? Y can be empty or not? Y can be empty or not? See, Y cannot be empty. Okay. Y cannot be empty. Why? Because if you take any string you take, okay, apart from empty string, don't worry about empty string. Okay. Do not worry. If you take any string, for example, okay, very simple point I'm saying, if you have a DFA, and let's assume this DFA has n states. In this DFA, you have n states. Now you take any string, okay, you take any string W. So some string W you take. Okay, understand this point. If you take this W string whose length is greater than n, greater than or equal to n. Now this is your W. Okay, you have n states. N states. Now what you do? Can you guarantee at least one state will repeat? Yes or no? You can guarantee that at least one state will repeat. Let's assume your string has length n. So you can guarantee that at least one state will repeat. You are starting in Q0, at least one state will repeat. Maybe this is this repetition. Okay, tell me, for this repetition, Y should be at least length 1. Yes or no? Can you notice? For this repetition, Y should have, okay, even if this repetition is like this, Y should have length at least 1. Okay, if you do this repetition, Y should have length at least 1. Yes or no? I mean, I will take care of your doubt, don't worry. But just understand this point. Okay, tell me, if you do this repetition, state will definitely repeat. If you do this repetition, Y will definitely have at least length 1. Yes or no? Length of Y will definitely be at least 1. I don't know where this repetition will happen. I don't know. I do not know where this repetition will happen, but I can say that if this repetition is happening, then Y has length at least 1. Okay, maybe this repetition is happening here. Maybe this repetition is happening like this. Now you can notice, now also this is Y. Now what is X? Now X is empty string. Now X is empty string, but Y will always have length at least 1. Correct? The length of Y will always be at least 1. That's it. Okay. So this is your pumping lemma. And now let me tell you the full statement. The full statement is like this. Okay. The statement one by one. Just okay. Look at the statement. Just look at the statement. Ananya, we cannot guarantee if your string has length less than n. I cannot guarantee anything. I cannot guarantee the repetition also. The repetition may happen, may not happen. I don't know anything. Just wait. Okay. But I can guarantee that if your string, you can notice, see, if you take a string of length less than n, then I cannot guarantee anything. I cannot say repetition will happen. Maybe repetition can happen. repetition may or may not can happen. Okay, so I cannot say anything, but here I can say, if your string has length at least n, if your string has length at least n, now I can guarantee that repetition will happen. Yes or no? I can guarantee repetition will happen. Correct? So that's the point. Yes, Digvijay, there can be many repetitions, but at least one repetition we can guarantee. Just focus on what we can guarantee. Can we guarantee more than one repetition? No, but we can guarantee at least one repetition. Correct or not? Are you getting my point? Okay. Are you getting my point? That I can guarantee at least one repetition. Just focus on what you can guarantee. Don't focus on what you cannot guarantee. Okay. Maybe more than one repetition can happen. Maybe. For example, if you take this, consider if you take this DFA. If you take this DFA, consider this is your DFA. Now you can notice that if you take this string PQR, okay, let's assume this is your string BAA. Consider this is your string. Now can you see from P to P, then Q to Q? So can you notice multiple repetition can happen, but I cannot guarantee this. Yes or no? I cannot guarantee that multiple repetition can happen, because see, multiple repetition may happen, may or may not happen, but I can guarantee at least one repetition will definitely happen. This is what I'm saying. At least one repetition will definitely happen. So this is the point. If your DFA, okay, so if you take this DFA has 3 states, this DFA has 3 states, and your string has length 3. You can notice your string has length 3. So I can guarantee at least one repetition will definitely happen. So in pumping lemma, always focus on what you can guarantee. Just focus on that. Don't focus on what you cannot guarantee. Okay, so this line, let me write. Okay, in this pumping lemma, basically, just focus on what you can guarantee. Okay, so what we can guarantee, what you can guarantee. So let me tell you what you can guarantee. If your DFA has n states and you take a string whose length is greater than equal to n, whose length is greater than equal to n, now I can guarantee that there will be repetition. Okay, so this is your DFA m, run m on w. I can guarantee at least in the state sequence, at least one state will repeat. Correct? In state sequence. This I can guarantee. At least one state will repeat. This I can guarantee. At least one state will repeat. Okay, this is the point. At least one state will repeat. Now tell me, even if more than one state is repeating, okay, now Digvijay is asking, how will I write XYZ? How I am going to write XYZ? This is a nice question. Now tell me, at least one state will repeat. Yes or no? At least one state will repeat. Correct or not? Tell me. Tell me, with n states, if you take a string of length greater than equal to n, now at least one state will repeat. Maybe more than one can repeat. Okay, maybe more than one can repeat, but at least one will repeat. Now just pick the first one repetition. Just pick the first repetition. Digvijay, just pick the first repetition. See, at least one state will repeat. Just pick the first repetition. Are you getting my point? See, okay, for example, here, for this string, at least one repetition is happening. This is also repetition, this is also repetition. Just pick the first repetition. Because I can guarantee at least one repetition will happen. So So pick the first repetition. Okay, now you can notice here. So if you pick the first repetition, just pick this P to P. So what is your Y? Tell me. Tell me what is your Y? Yes, this is your Y. You can notice very easily. This is your Y. So your Y is B, your X is empty string, and your Z is A. Is it clear? Tell me, is it clear? That's it. Just pick the first repetition because at least one repetition is guaranteed. We can guarantee at least one repetition. So you can pick the first repetition. Okay, don't worry, more doubts will clear. So now let me write the statement of pumping lemma and you just think about it and you tell me if your language is regular, if L is regular, does it imply that there is a DFA? If L is regular, then can I say there is a DFA? There is some DFA. There is some DFA, correct? Can I say, okay, any DFA will work actually, any DFA will work. Okay, there is some DFA. Any DFA, whatever DFA you have. Okay, let's assume this DFA has some finite number of states, yes or no? Yes or no? Let's assume this DFA has n states. Okay, so let's assume this DFA has n states, or let's call it p states. Let's assume this DFA has p states. Is it clear? See, one by one, step by step, I'm going. If your language is regular, then it automatically means that there is some DFA. Let's assume there are p states. Now, okay, if there is a string in L, okay, let's assume, okay, if W belongs to L with length of W greater than or equal to P, if there is any such string, then what can I guarantee? Tell me. If there is any such string, if W belongs to L with W length is greater than equal to P, then what I can guarantee? Then what I can guarantee? Basically, I can guarantee then in state sequence of W, I can say, then in state sequence of W, some state will repeat. Okay, some state will definitely repeat. Okay, so in this, so I can write W equal to XYZ. So what I can do, I can write W equal to XYZ. Yes or no? I can write W equal to XYZ. Remember, the first repetition I am focusing on, some state will repeat for first time. Yes or no? For first time, correct or not? Some state will definitely repeat for first time. Just look at the first repetition. Only look at the first repetition. Okay, now tell me if your state is repeating for the first time. Now, so I can write W like this. Yes or no? I can write like this. This is where repetition is starting. This is the part before repetition, and this is the part after repetition. Yes or no? This is your initial state, correct or not? This is your initial state. Tell me what is R? Tell me what is R? R is final state, because I am saying, I am talking about if W belongs to L. If W belongs to L, then this R should be final state or not? Correct? This R should be final state. Okay, so I can write W is as XYZ. Okay, such that you can notice that this is initial state, this is final state. Okay, now I can repeat this part Y any number of times. Yes or no? If I repeat this part Y any number of times, then from where I will go to where? From where to where I will go? Again, I will go from P to R, and R is final. Again, I will go from P to R. Yes or no? This I told you many times. If I repeat this Y, if I repeat this part Y, if I repeat it, any number of times if I repeat, okay. No, Sandeep, I am taking these strings. See this, look at this. I am taking only this string which belongs to L. I am only taking this string. If W belongs to L with W length is greater than equal to P, now because W belongs to L, because your string belongs to L, so this must be final state, yes or no? This must be final state, correct? So I can notice now if you repeat this Y any number of times, you repeat this Y any number of times, you can repeat this any number of times, you can repeat any number of times, okay. Again you will go from initial to final, yes or no? So can I say that x y power m z, can I say that this string belongs to L? Can I say this? Yes or no? Because I am going from initial to final, so again this will belong to L. And can I say length of Y is, what can I say about length of Y? That is greater than 0, yes or no? Basically Y cannot be empty. Y cannot be empty. This I told you. This I told you. Two things we have seen. Okay, two things. One last thing is remaining. What is the last thing? The last thing is remaining. Okay, just focus on this point, and your pumping lemma is over. The focus is like this. So your DFA has n states. Let's assume your DFA has n states, and you are taking a string whose length is greater than or equal to n. Let us assume your string has length a lot, a1, a2, a3, and let's assume this is an, and let's assume this is your aat. Let's assume. Okay, so your string can have any length greater than equal to n. You can notice your string has length greater than equal to n. Yes or no? Tell me. Your string has length greater than equal to n. Now tell me, where can you guarantee the first repetition? Where can you guarantee the first repetition? The first repetition, where can you guarantee? In the state sequence, the first repetition, where can you guarantee? Where can we guarantee the first repetition? Where can we guarantee the first repetition? Tell me, where can you guarantee? The first repetition, I am talking about first repetition. Where can you guarantee the first repetition? The first repetition is guaranteed within the Y, that is within here, yes or no? Within this area, the first repetition is guaranteed, yes or no? Tell me this point. This first repetition is guaranteed here, correct or not? Because why? Why? Because tell me, why the first repetition is guaranteed here? Why the first repetition is guaranteed here? Because in this part, in this much part, you will have n plus 1 states. In this much part, you will have n plus 1 states. Okay, and total you have n states. So in this part, you can guarantee the first repetition. Just tell me this point. Total you have n states. Total you have n states. Okay, and this is your state sequence. This is your state sequence. In this state sequence, we have total t plus 1 states. Total t plus 1 states we have in this state sequence. But what I am saying you have total n states. So within this part, within this much part, I can guarantee the repetition. Yes or no? Because within this part, I will have n plus 1 states, but I only have n states. So within this part, at least one repetition is happening. So this is the point. If you can understand, that's it. So basically, I'm saying that, okay, DFA with n states, okay, run on W with length of W greater than equal to n. Then in the state sequence, we can we can guarantee the first repetition. I'm talking about the first repetition. We can guarantee the first repetition of state will happen within first n symbols. Yes or no? Within first n symbols. Correct? Yes or no? So that's the point. That's the point. So okay, within first n symbol you will get your y. This is what I'm saying. A1, A2, A3, AN, then AN plus 1 and so on, AT. This is your W. Okay. Now what I'm saying that within your first repetition will definitely happen here. So your y will be within these first n symbols. Yes or no? So I can say my y will be somewhere here. I don't know where. I don't know. Maybe y is here. Maybe this is y. I don't know. But I can guarantee that y is within the first n symbols. The first n symbols. Y is within the first n symbols. So what can I say about length of xy? You know, length of xy. What can I say about length of xy? Yes, that is less than equal to n. Because y is within here. For example, maybe y is here. Maybe this is y. Maybe this is y. Okay, I don't know where is y, but let's assume this is y. Then this is x. And then this is z. So you can guarantee that the length of xy will be less than equal to n. Is it clear to everyone? Tell me. This is your pumping lemma. Is this clear? So now let me write the pumping lemma. So the complete statement I'm writing, okay, the proof we have seen. This is the proof we have seen. And now I'm writing the statement that for any regular language, or you can say if L is regular. Let me write if L is regular. If L is regular, then there is a DFA, yes or no? Then there is a DFA. Okay, L is regular. If L is regular, then there is a DFA. So I can say that, okay, what I can say, if L is regular, then there exists some number P. See, if L is regular, what can you say about number of states in L? You only have L, okay, and you only have this information. I am not giving you which regular language. Then what can you say about number of states in DFA? Can you say they are 100? Can I say 100? Can I say 200? No, that will depend on L, yes or no? But I can say some finite number. I can say some P belongs to natural number, yes or no? At least one string, at least one state will be there. Some natural number I can say. If L is regular, then you have DFA. I don't know how many states this DFA has. Okay, but I can say number of states in this DFA. What I can say, number of states, let's call it P. Then that P belongs to L. This I can say some finite number of states you have. So that is the point. If L is regular, then there exists a P. Then there is a magic number. Okay, we will call it magic number. Then there is a magic number. Okay, after some time I will tell you, but let me write like this. Then there exists P belonging to set of natural number. There exists some P. Okay, there exists some P such that if W belongs to L, where W has length greater than equal to P, then what should happen? Tell me. What should happen? You can notice if L is regular, then there exists some P. Belonging to L such that if W belongs to L, okay, such that W has length greater than equal to P, then W can be W can be split. W can be split into three parts. Into three parts, X, Y, Z, such that what will happen? What will happen? We can partition W into three parts such that length of Y is greater than equal to 1, length of XY is less than equal to N, less than equal to P, because we are taking P, that is less than equal to P, and X, Y power I, Z, that belongs to L for all I greater than equal to 0. All the proof we have seen, all these three properties, the proof we have seen. So tell me, are they clear? These three properties, now are they stuck in your mind? These three things, are they stuck? The Y, you have this part Y, which you can repeat any number of times. Basically, this part Y, this you can repeat any number of times. We can repeat it any number of times. Correct? If I give you regular language, if I give you some language, you don't know about, it's DFA. This P actually, after some time I will tell you, this P depends on language. Just wait. This P is some number. Y length of XY is less than equal to P. This we have seen, right? Within the first P symbols, you can think like this. P is basically the number of states. You can think like this. After some time I will tell you that P can be less than number of states also. But you can think your P is number of states. Yes or no? Your P is number of states. So we have seen that within the first, let's assume your P is N. Your P is number of states. Is it clear, Ananya? Within the first P symbols, you will have your first repetition. This is what we have seen. Within the first P symbols, Y is within first N symbols. Is it clear? So this is the point. Let me make it easy. The proof we have seen, but after some time I will tell you that actually, let me tell you. See, what is P basically? Let us see what is P. What is this P? Actually, just wait. You can notice one thing. P is definitely less than, P is definitely less than equal to number of states in minimal DFA, yes or no? Why? See, because in the proof you can see that this N is what? Number of states. Yes or no? In this proof, this N is number of states. What is this N? This is number of states in DFA. Number of states in any DFA. So I can say that I can take minimal DFA, yes or no? So I can take minimal DFA, correct or not? I can take minimal DFA, correct or not? I can take minimal DFA, yes or no? I can take minimal DFA, I can take. So this N I can take as number of states in minimal DFA, yes or no? I can take it as number of states in minimal DFA. So what I am saying is that actually this P can be any. This N can be number of states in any DFA. This can be any DFA. So you can take minimal DFA also. But so from here I can say this P is your basically, what is P? Actually, let us assume your minimal DFA has assume N is regular. Then you have minimal DFA. and let's assume you have minimal DFA has n states. Let's assume your minimal DFA has n states. Tell me one thing. If your minimal DFA has n states, then I can take this P to be any number greater than equal to n, yes or no? I can take this P because this P can be number of states in any DFA. Number of states in any DFA. So this P can be taken as any number greater than equal to n. Any number greater than equal to n will work. But okay, this P can be depending on the language. Depending on language L, this can be less than equal to n also. This can be less than equal to n also. After some time we will see. But this is guaranteed. This will definitely work. This is guaranteed. But this we cannot guarantee. It will depend on the language. Okay, it will depend on the language. But this is guaranteed. That you can take P to be any number greater than or equal to n. See, Ananya, within the first, okay, just say this. See, in this W, within the first n symbols you have y, yes or no? A1, A2, A3, an plus 1, at. Within the first P symbols you have y, yes or no? Your y is within these, yes or no? Tell me. So your y is within these. Let's assume, I don't know where is y. Let's assume this is y. Is it clear? Your y is within the first n symbols, correct or not? Your y is within the first n symbols. This we have already seen, right? Right? This we have already seen. Correct or not? Now you can notice your y is within here. I don't know where. Maybe y is here. Maybe y is this. Maybe y is this. Maybe y is this. Then what is x? If y is this, then what is x? Then x is a1. Yes, very good. Then x is a1. Can you notice the length of xy is less than equal to n? Can you notice? Your y is within. I am not saying y has length n. I am saying y is within first n symbols. Okay, maybe your y is here. Maybe your y is this. Maybe this is your y. Maybe this complete thing is your y. Then what is x? Maybe this complete thing is your y. Then what is x? Then x is epsilon. No, not phi. X is epsilon. X is a string. Then x is epsilon. Correct? If your y is this, let's assume your y is this. This is your y. Then what is your x? If this is your y, then what is x? Then x is a1, a2. Can you notice that y is within first n symbols? Y is within first n symbols. Also, can you notice now a length of xy is less than equal to n? Because length of xy cannot go beyond this. This xy part cannot go beyond this. Okay, this xy part, this cannot go beyond this. That's it. Okay. So now what I'm saying, what is this P? What is this P? So this P is pumping length. We call it pumping length. You can notice that definitely if you have a regular language, then you have minimal DFA, and let's assume your minimal DFA has n states. Now I am saying that any number greater than equal to n will work. Yes or no? Any number greater than equal to n will work as pumping length. Because we have DFA of size greater than or equal to n for any. Okay, we have DFA of size m where m is greater than equal to n. Correct or not? See, your minimal DFA has n states. your minimal DFA has n states, but you can create DFA with n plus 1 states also. Yes or no? You can create DFA with n plus 2 states also. You can create DFA with n plus 3 states also. Yes or no? Tell me yes or no. So you can create DFA with any number of states. You can create any number greater than equal to n. You can create DFA. Yes, correct. Minimal DFA has these many states. So, and you're okay. And in the proof you have seen already, in the proof you have seen that number of states of DFA, they will work as P. Yes or no? Number of states of any DFA will work as P. Is it clear? Number of states of any DFA will work as P. So, if minimal DFA has n states, then any number greater than equal to n will definitely work as P. Namrata, I am saying any number greater than, I am saying if your minimal DFA has 10 states, then do we have DFA with 11 states? Let's assume for this language, you have minimal DFA with 10 states. You have minimal DFA with 10 states. Do we have, for this language, do we have DFA with 11 states? Do we have some DFA with 11 states? Yes, of course. Just put any extra state, unreachable state, you can put whatever you put. Okay, yes, of course. Do we have DFA with, so I can say we have, basically I can say we have DFA with m states. We definitely have DFA with m states, where m can be any number greater than equal to 10. Yes or no? For this language, we have DFA with m states, and this m can be any number. We have DFA with 11 state, we have DFA with 12 state, we have DFA with 20 state, we have DFA with 100 state. Correct or not? So if you have minimal DFA with 10 state, then any number greater than or equal to 10, any number greater than or equal to 10, we have a DFA of that size for L. Okay, with examples, these points will be clear. So far, whatever you got, okay, just wait. All the points will get clear. Now let me just go and let me write the pumping lemma. Now the proof is okay. You have known the proof. I told you the proof. Now forget about the proof. Are you getting my point? Proof I told you so that you understand the pumping lemma. Now for for few moments, for 1 hour, just forget about the proof. Okay. So now just understand this statement that I am saying. A theorem I am saying, this statement you understand. Are you with me? I told you the proof, but for 1 hour, forget about the proof. Just understand this statement, and then we will solve questions. Yes, okay, just let me, okay, so let's take a break, and after the break, we will continue. Please just wait. Okay, let me give you, okay, let's take a 6 minutes break. After the break, we will continue. Just wait. Okay, let me, Namrata, just wait. Okay, anyone has any doubt, just wait. Let me answer some examples. Let me take some examples. All these points will clear. Hi everyone. Okay. Let's start. So what we are going to do, we have seen proof. Now let me give you a statement and then let's do some examples. And after those examples are over, once you are comfortable with pumping lemma, then we will take the proof again. Okay, so let's see. The statement is very simple, that if L is regular, this is the statement of pumping lemma. If L is regular, then there exists a number P. There exists a number P greater than or equal to 1. I can say there exists a number P, okay, greater than or equal to 1, such that for all strings in L whose length, okay, for all strings in L whose length is greater than, for all strings in L whose length is greater than P, okay, we can split W into 3 parts, W into X, Y, Z, such that length of Y is greater than equal to 1, length of X, Y is less than equal to P, and you can say, and okay, X, Y power I, Z belongs to L. Okay, for any I greater than equal to 0. Okay, for any I greater than equal to, basically you can repeat this part Y. Okay, actually we can simplify this statement. Okay, let me simplify this statement. So what this statement is saying is that for any regular language, let me simplify, and this simplified statement we will use. If L is regular, then there exists, yes or no, then there exists a P, there exists a magical number, let's call it magical number. Okay, so let's call it pumping length, or you can call it magical number. So this P we will call it pumping length. So there is something called pumping length. So you can notice, if L is regular, then there exists a pumping length P greater than equal to 1, okay, there exists a pumping length such that for any string of L, for any string W of L with W's length is greater than equal to P, okay, within the first P symbols of W, this line, okay, this we will use within the, basically this property, if you see this property I am using, this property saying that within the first P symbols, yes or no, within the first P symbols of W, we have some non-empty. I'm talking about Y. You can notice Y is non-empty. So I'm talking about Y. So within the first P symbols of W, we have some non-empty substring. Y, which can be repeated any number of times. And the resulting string must belong to L, yes or no? Which can be repeated any number of times, and the resulting string belongs to L. So you repeat it any number of times, the resulting string belongs to L. So this statement we will use. Is it clear to everyone? Just read this statement. Sandeep, I will tell you. Okay, don't worry. I will tell you. Right now, in your mind, you think, just read this statement. Is this statement clear? Is this statement clear to everyone? If L is regular, then there exists a pumping length. There exists some P, some magical number P. Basically, for every regular number, for every regular language, if you have a regular language, then for this regular language, there is a magical number. I don't know what is that magical number, but there is a magical number. There is a magical number P. There is some magical number P. Okay. So we have some magical number P, some magical number P we have, okay, such that if you take any string of L, if you take any string from here whose length is greater than or equal to P, whose length is greater than this magical number, any such string you take, any such string can be pumped. So from this L, you take from this L, W should belong to L. Okay, remember, this is important. W should belong to L. W's length must be greater than or equal to P. Any such string, any such W can be pumped. Can be pumped. Pumped means repeated, basically. Can be pumped. What do I mean by pumped? I mean pumped means any such string which is in language also whose length is greater than or equal to P. Any such string can be pumped. Pumped means this part can be repeated any number of times. Okay, and this Y is within the first P symbols. Within the first P symbols, you will find this Y. Clear? So let's take example. So okay, so now let me take example, and with example all these concepts will become more clear. So consider the first example. Consider this language. Okay, A starting with A. Okay, consider this language starting with A. Okay, let's assume your sigma is A comma B, and consider this language starting with A. So what is your language? Can you tell me? Your language is basically AB star. Yes or no? Your language is A, AB, AA, like this. So your language is basically A plus B whole star. This is your language. Okay. Now for this language, do we have, okay, forget about all the things. Just okay. Just we are going to apply this pumping lemma. Okay. So do we have some magical number? Let me give you a magical number 2. Let's check it out. Let's check whether 2 will work or not. Okay, let's check. Okay, let's check whether P equal to 1 will work or not. Will it work? This magical number will work or not? Tell me. Let's check it out. Okay, see, check it out. So any string you take from L, any string from L you take whose length is greater than or equal to 1. So I can take A, yes or no? Any string from L you take whose length is greater than or equal to P, whose length is greater than or equal to P. So I can take A. I can take A, yes or no? Within the first P symbols, okay, means within the first one symbol, okay, I have Y. Okay, I have non-empty substring. So that non-empty substring should be Y. This must be, okay. Like I have no other choice, yes or no? I have no other choice. Okay, so Y must be this, because within the first one symbol, I must have non-empty substring. I must have. Arey Sandeep, forget about state, please. This is what I am saying. I am again requesting. I told you the proof. Forget about proof. I told you the proof. Forget about it. Please focus on the statement. A statement I have given to you. Focus on that statement. After some time, I will tell you what is the relation between this statement and the proof. Okay, why basically, what is, okay, all the things I will tell you. Just focus on the statement. So your statement says that there is magical number. If your L is regular, then there is magical number. There exists a magical number. There exists a magical number. Okay, now such that if your W belongs to L, whose length, your W, whose length is greater than or equal to P, then within the first P symbols, you must have some Y. Some Y must be there within the first P symbols. Correct? Okay, so tell me here. Let's check whether P equal to 1 will work or not. So tell me, will it work? So I have no other choice. This must be my Y. This must be Y, because Y cannot be empty. Non-empty substring. So this must be Y. Can I repeat it 0 times such that I will get, can I repeat 0 times? If I repeat 0 times, will it belong to L? if I repeat 0 times, if I repeat this y 0 times, so your x is what? Tell me for this string, this is your y. You can notice this is your y. X is epsilon and z is epsilon. Clear? X is epsilon, z is epsilon. If I repeat this y 0 times, basically x y power 0 z, that means epsilon. Does it belong? Okay, that does not belong to L. Yes or no? So this will not work. So can I say p equal to 1 will not work? This magical number will not work. Yes or no? Because if I take this magical number, then you can notice that if I repeat this y 0 times, then string does not belong to result does not belong to L. So this will not work. Now let's check whether this magical number will work or not. Will it work? P equal to 2. For p equal to 2, which strings you will check? Will you check A? Will you check A? No, because you have to check only these strings. Only check these strings which belong to L and whose length is greater than equal to P. Okay, so let's check. Okay, in this string, do we have Y? Within the first two symbols, do we have Y which can be repeated? Okay, for this string, what are the possibilities of Y? Within the first two symbols, there must be Y. If I take Y equal to A, if I take Y equal to B, if I take Y equal to AB, which I can take? Tell me. I have these three possibilities. Which possibility will work? Which possibility will work? Yes, this possibility will work, right? This possibility will not work. This will not work. This possibility will not work if you repeat this, if you do this. If you do this, then this will not work. This will not belong to L. Similarly, this will not work. This Y will not work. Because again, if you do this, then that does not belong to L. But this will work, yes or no? This will work. Correct or not? This will work. Now you can notice, you can pump this, okay, A, B. So this is your X, this is your Y. Now you can repeat this B any number of times and your Z is epsilon. Repeat this any number of times. If you repeat 0 times, you will get this. If you repeat this 0 times, if you repeat I 0 times, if you repeat 1 time, you will get this. If you repeat 2 times, you will get this. If you repeat 3 times, you will get this. All of them, they belong to L, yes or no? You can repeat any number of times. You can repeat any number of times that will belong to L. Correct? Tell me yes or no. Is it enough? This will not work because if you put Y, if this is your Y, Ananya, if this is your Y, then if you repeat it 0 times, then epsilon does not belong, yes or no? If you take this as Y, this is your Y, if you repeat it 0 times, repeating 0 times means removing it. So basically epsilon does not belong, yes or no? So can you notice, is it enough? Can I say P equal to 2 is your pumping length? Yes, very good, Sandeep, very good. So that is the point. We only have checked this string. Actually, for all strings, this should work. For all strings of language, this should work. So will it work? Okay, this is what I am asking. This is your language, A plus B whole star. Will this work? Will this work for all strings? Will work for all strings W of L such that W length is greater than equal to 2. It will work. Why it will work? Tell me. It will work actually. It will work because what you can do, you can take the second symbol. You can take second symbol as Y because for any such W, you can take second symbol as Y. Yes or no? You can take whatever string you take, you just take second symbol as y. Just take this symbol as y. This symbol, this second symbol you can take as y. Okay, this is your x and the remaining is your z. So you can notice this p equal to 2. Now can you notice, if you repeat this second symbol any number of times, I will get the result in the language, yes or no? If I repeat this second symbol any number of times, if I repeat this, still the language is, still the string is starting with a. Are you getting this point or not? So basically, if I take this second symbol, let's call this second symbol y. So if I repeat this second symbol any number of times, then you can notice this still belongs to L. So I can say p equal to 2 will work, correct or not? P equal to 2 will work. So for this language, what I'm saying is p equal to 2 will work, yes or no? So p equal to 2 is working. Tell me yes or no. It is working, yes or no? For this language, p equal to 2 is working, correct? Any number greater than 2 will also work. See, if p equal to 2 is working, then any number p, any number greater than equal to 2, will also work. Why? See, if p equal to 2 is working, then any number greater than equal to p, any number greater than equal to 2, for example, p equal to 3 will also work. The same way, in p equal to 3, what you will do? Again, you can take the second symbol. The same way it will work. Okay, so it will work. Can work in same way. Can work in same way as p equal to 2. Okay, the same way. Again, what you do? The first symbol is your x. Again, the second symbol is your y, and the remaining thing is your z. You can notice within the first three symbols you have y. Yes or no? Tell me yes or no. Yes or no? Within the first three symbols you have y, because second symbol, this is your second symbol. The second symbol is your y. So you can notice all the properties are satisfied. So p equal to 3 will also work. The same you can do. So p equal to 4 will also work. The same way as p equal to 2. Again, what you can do? First symbol is your x, second symbol is your y, and the remaining string you can take as z. You can notice within the first four symbols we have y. Is this clear to everyone? Now let us make a DFA. For this language, how many states I will get in the DFA? No, why? There exists a y. Ashish, there exists a y. You can have, there exists a y. I am not saying for all y. There exists a y. Focus on that. There exists a y. I can give you this y. There exists a y. There exists a non-empty substring. Focus on this. Okay, just wait. Some more examples. Let's make the DFA for this language. How many states in the DFA? Tell me how many states in the DFA. In the DFA, you will have how many states total? Starting with how many states you will have? 3 states you will have. Why are you forgetting this? 3 states you will have in the minimal DFA. In minimal DFA, you will have 3 states. You have 3 states in the minimal DFA. Now, do you remember the proof of pumping lemma? Pumping lemma proof, do you remember? So you can notice definitely, because minimal DFA has 3 states, so this 3 will work as P, yes or no? This proof I told you, in the proof I told you that the number of states of DFA will work as P. What I told you, you can notice, okay, for this language, consider this language, for this language, we have DFA with 3 states, okay. So now you notice, so let's call it P, let's call this P, okay. So let's call this number of states P. Okay, now you can notice, if you take, so your P is 3, you can notice that if you take any string, so let's call this P, so your P is 3, number of states, that is your number of states. Now you tell me, in this DFA you have 3 states, so if you take any string, for all strings, if you take any string W belonging to L whose length is greater than or equal to 3, what will happen? Tell me. What will happen? You can notice, if you take any string belonging to L whose length is greater than or equal to 3, then in state sequence, we have repetition, yes or no? We have repetition, at least one repetition. We have at least one repetition. And that repetition, the first repetition, where can I find? The first repetition, where can I find? We have repetition. The first repetition I can find within first 3 symbols, yes or no? Within first 3 symbols. The first repetition I can find within first 3 symbols. Within first 3 symbols I can find. Yes, within first 3 symbols I can find that repetition. That's it. So basically, if you take any string whose length is greater than or equal to 3, then you have repetition. The first repetition, okay, so you have repetition. Now you can notice this first repetition. This first repetition, it will happen within the first n symbols, correct? Within the first 3 symbols it will happen. Within the first 3 symbols it will happen. So that's it. So can you notice the proof is very similar to the pumping lemma statement? Yes or no? Now you can notice very easily, now all the things. Now what you can do? Now you can repeat this y any number of times. This is your x, this is your z. Now you can repeat this y any number of times. Still you will go from Q0 to QF. You will go from Q0 to QF. So you can notice that. You can repeat this any number of times. You will go to language L. And this y, you know the length of y, that is greater than or equal to 1. And within the first n symbols, so the length of xy. Tell me, what is the length of xy? The length of xy must be less than or equal to 3. Correct or not? Because within the first 3 symbols you have y. There exists a y. Correct or not? Yes or no? But the point is very simple. If you make the DFA, then definitely. But you can notice that, okay, for this language, we have seen that this will also work. See, if you make DFA, then you will know that, okay, 3 will work. So, okay, if you go by DFA for this language, if you go by DFA, then what P you will get, tell me? Then you will get P equal to 3, P equal to 4. So P equal to 4, these things you will get, yes or no? These things you will get, correct or not? for this language, if you go by DFA, then you will get these values of P. Correct or not? But can you notice that P equal to 2 will also work. But for L, can you notice P equal to 2 will also work? This we have already proven. Yes or no? This we have already seen that P equal to 2 will also work. So can you notice one thing? Just notice one thing, that this P depends on language, not on DFA. This point I want to say. Can you notice? Of course, these will definitely work. No problem. These will work. But the point is, this P will depend on language, not on DFA. The proof depends on DFA, but this P, this pumping length will depend on language, not on DFA. So this is important. So pumping length is property of language, is property of regular language, is property of language, I can say, not of DFA. So basically the pumping length, that depends only on the language. Is it clear? Because 2 will also work, 3 will also work, 4 will also work, 5 will also work. So I can say that for this language, P greater than equal to 2, any number P greater than equal to 2 is pumping length. So pumping length depends on language, not on DFA. Pumping length is property of language. Is it clear to everyone? So that is the reason I was telling you please. Okay, actually what I say now, finally I just want to say, if you understood all of it, then it is good. Okay, else just understand this statement, because I don't think that I can make you understand more than this. Okay, but please focus on this statement that I am giving you, and this statement we will use. Many things I have told you, proof I have given you. Okay, I have tried to make you understand this, but now let's focus on this statement and just focus on it. Okay, this is the statement of pumping lemma. Pumping lemma for regular languages. For regular languages. This statement, okay, just understand this statement. If L is regular, then if L is regular, then there exists a magical number. Then there exists a magical number. We will call it pumping length. So you can notice, if L is regular, then there exists a magical number P. Okay, if L is regular, then there exists a magical number P greater than equal to 1. Okay, there exists a magical number P greater than equal to 1. Just understand each one of them, each statement. If L is regular, then there exists a magical number. There exists a magical number. Okay, there is some, maybe 1,000, maybe 1 lakh, maybe 1 crore. I don't know. There exists a magical number P greater than equal to 1, which depends only on the language. This important line, because many people don't understand this. So which is property of language, not of DFA. Pumping length is property of language. It is not property of DFA. So which depends solely on language. Which depends, I can say, solely on language. Which depends on L only. Okay, so which depends on L. So, but the point is, there is a magical number. There is a magical number P greater than equal to 1, such that for all strings this will happen. This is important. for all W belonging to L whose length is greater than equal to P. For all these strings, let's call them, okay, let's call them candidates. Let's call them candidate strings. Let's call them, this name we give them, okay. Let's call them candidate strings. So for all these strings, what should happen? For all these strings, W can be, there exists a partition, okay, I can say, for all these candidate strings, for all candidate strings, what happens? There exists a partition, there exists a split. There exists some split. There exists some split. W equal to XYZ. There exists some split W equal to XYZ such that what three properties must be there? Such that this Y is non-empty. This Y should be non-empty. This Y should be non-empty. Means Y should be non-empty. Okay. And length, and this Y should be within the first P symbols. And this Y can be repeated any number of times. And the result should belong to L. Is it clear to everyone? This statement, is it clear? So within the first symbols, remember, okay, remember within the first P symbols, you must have Y, which can be repeated, which can be pumped. Clear? This is the statement of pumping lemma. What we have seen so far, that was proof, that was idea, intuition, so that you can visualize, okay, from where these conditions are coming, what is happening, okay, why it is happening, all these things you can visualize. But the final point is this is pumping lemma. Okay, if you understand this statement, these three slides, this one, this one, this one, if you can understand these three, if you understand this definition, then you can understand you can solve all the questions. Okay, is it clear? So let's take this example, 0 power n, 1 power n. You know this is non-regular, right? Consider this language. This I told you in the last class, 0 power n, 1 power n, n greater than equal to 0. In the last class, I told you this is non-regular using Mahil-Nerod theorem. We used Mahil-Nerod theorem and we proved this is non-regular. Yes, Rasi. If you repeat 0 times, then basically it means, okay, remember, repeating by 0 times, what it means? Repeating by 0 times means removing Y. Basically means remove Y, or you can say basically Y power 0 is epsilon. So x Y power 0 Z, that is basically same as xz. So repeating by 0 times means you are doing like this, and repeating by 2 times, that means this is repeating by 2 times, repeating by 3 times, 4 times, like this. Now okay, just understand this. This is your language. You know this is non-regular, but let me prove using pumping lemma. Tell me, assume this is regular, then what should happen? Assume L is regular, then what should happen? If L is just assume this is regular, then there is a magical number, yes or no? Assume L is regular, then there exists a magical number. Then there exists a magical number. Then there exists some magical number P. Yes or no? Some magical number P there exists. I don't know what is this. Do I know this? Do I know what is this? Can I take P equal to 10? No, because I don't know what is this P. Okay, just focus. I don't know what is this P. There exists a magical number P. Such that what should happen? Such that if you take any string such that, okay, for all W whose length is greater than equal to P, they must be pumped, yes or no? For all such W must be pumped. All such W must be pumped. For all W whose length is greater than P, W must be able to pump. I can write like this and I can pump it. So W can be pumped. Now, let me tell you that you take any P, you take any random P. So let's assume, so this is your P. Now, this string should be pumped or not? Tell me, 0 power P, 1 power P. This should be able to, this is candidate string or not? Tell me, is this candidate string? Yes, because it belongs to the language. You can notice this belongs to the language. Also, the length of this is greater than or equal to P. So this is candidate string. So this should be pumped, yes or no? You can notice I am assuming P is pumping length. This is I am assuming. This P is pumping length. I don't know what is this pumping length. So let me assume P. Now, whatever P you have, this string should be pumped. Because this string belongs to the language. Also, the length of this string is greater than P. Within the first P symbols, you should find Y. Yes or no? Yes or no? Within first P symbols, somewhere we have Y. Yes or no? Somewhere we have Y. We have some Y which can be repeated, which can be pumped, yes or no? Which can be repeated. Pumped means repeated. So within the first P symbols, so this is your W. Your W is this 0 0 0 0 and 0 and 1 1 1 1 and 1. So these are P symbols. Yes or no? These are the first P symbols. Within the first P symbols, in this area, you must have somewhere you must have P. Yes or no? Correct? Somewhere you must have P, or somewhere you must have Y. You must have Y. I don't know where, but Y must be here. I don't know where. Okay. I don't know where. So, but okay, tell me one thing. Where in this area, where is Y? Can I take Y equal to 0 power K? Like, I don't know where is Y. I do not know where is Y, but I know Y is here. For example, this is, let's assume this is Maharashtra. I don't know where is Y, but I know Y is within Maharashtra. It's like this. So in this area, we have Y. So can I take Y equal to 0 power K, where K is greater than or equal to 1 and less than or equal to P? Yes or no? I don't know where is Y. So can I take Y equal to 0 power K? Maybe Y is this. Maybe Y is this. Maybe Y is this. Maybe Y is this. I don't know. So can I do this? Y equal to 0 power K, where K is greater than or equal to 1 and less than or equal to P. I can take this, yes or no? Tell me yes or no. So what can I write W? If I take this as, so what can I write W? W is basically, what is W? W is 0 power P minus K, 0 power K, Z. Yes? Yes or no? This is your X, this is your Y, and the remaining thing is Z. The remaining is Z. The remaining is Z. Now, if I repeat this Y 0 times, what I will get, tell me? Repeat Y 0 times. What I will get, tell me. What I will get if I repeat this 0? If repeat 0 times means just remove it. Just remove. Repeat 0 times means just remove it. You repeat it 0 times. This is your Y. Your Y is this. This is your Y. You repeat it 0 times. What you will get? You will get 0 power P minus K. You will get this 0 power P minus K Z. Can you notice? Number of 0 has decreased by at least 1. Yes or no? Can you notice? Because this K is greater than or equal to 1. So number of 0 has decreased by at least 1. So I can say in this string does not belong to L. Because why? Because number of 0 in this string, let's call it string S, then number of 0 in this string S, that is less than equal to, that is less than P. Yes or no? That is less than P. Because at least 1 0 has gone. If you repeat this Y 0 times, then at least 1 0 has gone. At least 1 0 has gone. At least 1 0 has gone. Yes or no? And 1 cannot go. Okay. Ones are as it is. Yes or no? Ones are as it is. Because they are out of this area. They are not in the area of Y. The area of Y is this. This is the area of Y. These are out of area of Y. So you can notice the number of zeros are less than equal to P, and number of ones are as it is. They are as it is. So I can say this string does not belong to L. Is it clear? So I can say that whatever P you take, notice that for this language, 0 power P, 0 power N, 1 power N, N greater than equal to 0. Whatever P you take for this language, whatever P you take, W equal to 0 power P, 1 power P cannot be pumped. By any Y. Yes or no? This cannot be pumped by any Y. So what can I say? So I can say this is non-regular. Yes or no? Because if it is regular, then it should be pumped. Yes or no? If this language is regular, then it should be pumped. So L is non-regular. Yes or no? Because if it is regular, then it should be pumped. Is it clear? Tell me, is this proof clear to everyone? Pumping lemma. Let's take example. Another example. Okay, consider this. This language, number of A's is equal to number of B's. Is equal to number of B's. Consider this language. Okay, consider this language. Now, using Myhill-Nerod theorem, I told you this is non-regular. Yes or no? Did I tell you? Using Myhill-Nerod theorem, I told you in the last class, I told you this is non-regular. Okay, we have already proven that this is non-regular, and you already know this is non-regular because we have to find how many A's are there, how many B's are there. We have to count number of A's, number of B's. We have infinite possibilities. Yes, very good. So because for this language, you have infinite possibilities. Infinite possibilities. What are those infinite possibilities? For example, these infinite possibilities you have. For example, a power 1, a power 2, a power 3, a power 4, and so on. These infinite possibilities you have. Okay, yes or no? So you have infinite possibilities. So this is non-regular. Now this language we will prove using pumping lemma. Let us assume this is regular. Assume this is regular. Then what should happen? Assume L is regular. What should happen? Tell me. Then there exists a magical number. Yes or no? There exists magical number P. Correct? Okay. There exists magical number P. Now, every string of L. So, okay, for all strings of L whose length is greater than equal to P, that can be pumped. Yes or no? That can be pumped. That should be able to pump. We should be able to pump it. It should be able to pump. Now, okay, you can notice that whatever P you take, you can notice this string cannot be pumped. Again, you can notice this string cannot be pumped. Again, you can take the same string. Whatever P you take, this string cannot be pumped. Yes or no? Again, the same thing. This cannot be pumped because within the first P symbols, you must have Y. Within the first P symbols, you must have Y. Your Y must be within the first P symbols. Your Y must be here. Okay, your Y must be here. So it means Y must have at least one A. Y must have at least one A and no 0 and no B. Yes or no? Y must have at least one A. At least one A. Y must have at least one A. And Y must be within this area. Within this area, Y must be. So your Y must be in this area. Okay. And Y must have whatever Y you take, it must have at least one A. Now, if you repeat this Y 0 times, then what will happen? If you repeat this Y 0 times, you can notice this will not belong to L. Why? Because at least one A is gone. Yes or no? At least one A is gone. But number of B's are as it is. Yes or no? At least one A is gone, but number of B was as it is. So I can say that whatever P you take for this language, okay, this is your language, this is your language. For this language, whatever P you take, this string, this candidate string cannot be pumped. So it means your contradiction, yes or no? So it means this is non-regular, because if it is regular, then we should be able to pump it. If it is regular, then we should able to pump it. Correct? Sandeep, I have given you counter example. We just, okay, actually in pumping lemma, we just need to find counter example. We are trying to find the counter example. Yes or no? For example, okay, consider this language again. The same language you consider again. W such that number of A's is equal to number of B's. Now assume that I take this string. Assume you take P. Assume you regular. Assume L is regular. Okay. Okay, so for this language, let's assume some student X does this. Okay, some student S does the following. Okay, some student X does the following. So this is your language. Now what student S is doing? Student S is doing this. Student S is taking, assume, okay, this L is regular. So he is assuming L is regular. First he is assuming L regular. Now what he is doing? Now this student is doing, okay, so there must exist a P. So there exists a magical number P. So far so good, yes or no? So far no problem. So there exists a magical number P. Okay, such that all the strings must be able to pump, yes or no? All the strings, such that all the strings W whose length is greater than equal to P, which belong to L, they must be able to pump, must be able to pump. So far so good. So far no problem. So far there is no problem. Yes. Okay. Now what this student is doing? This student is taking this string. Okay. A B power P. This student is taking this string A B power P. Is it candidate string? Tell me. Is it candidate string? Yes. You can notice W belongs to L, and you can notice length of W is greater than P. So this string, this student is taking. So this student S, he is taking this string. Which string he is taking? This string. And now this student is saying, can we pump it? AB, 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 AB. Can we pump it? Within the first P symbols. Within the first P symbols, can we find? Within the first P symbols, can we pump it? Within first P symbols. Within first P symbols, can we pump it? Tell me, can we pump it? Can you have Y? Yes, you can take this as Y, yes or no? You can take this as Y. Tell me yes or no? You can take it as Y. If you take it as Y and you repeat it any number of times, the resulting string will belong to L, yes or no? Take it as Y. Take this as Y. Okay. Take this as Y. So you can pump it right, yes or no? So for this string, there exists a split. Yes or no? There exists a split X, Y, Z, such that your Y is basically AB and your X is also AB and your Z is remaining. So your X is also AB. This is your X, this is your Y, and this is your Z. This is your X. So tell me, if you repeat this Y any number of times, will it belong to L? If you repeat this any number of times, if you repeat this, will it belong to L? Yes, it belongs to L. Yes, it belongs to L. So now the student is saying that, okay, so you can notice this string I can pump. So language is regular. So L is regular. Is it correct logic? Is this correct logic? This student S can pump this string. He can pump this string. So can I say L is regular? So I can say L is regular? No. Okay. Answer is no. Why? What is the reason? What is the wrong with the student S argument? Yes, very good, Sandeep. Because this student S only has proven for this. Student S has only taken this type of string. But we should, okay, for all string, we should be able to do this. For all string, we should be able to do this. Okay, so you can notice no, because for all W belonging to L, whose length is greater than or equal to P, we must be able to pump. We must be able to pump. But for any P, W equal to A power P, B power P is counter example. So L is not regular. Is this clear to everyone? Is this correct? Clear? So let me tell you a few things. Okay, this pumping lemma, okay, you understand this pumping lemma. First of all, this pumping lemma, let me write as quantifier. Can you notice? For all regular languages, let me write this pumping lemma as quantifiers. Pumping lemma definition in first order logic, using first order logic. Using first order logic. Let me write using first order logic. Okay, tell me, for all regular languages, it should happen, yes or no? For all regular languages, yes or no? For all regular languages, yes or no? Tell me. So using, okay, so let me write like this. For all regular languages L, where L is regular language. For all regular languages, where L is regular, okay? So I can say for all regular languages. Correct? What should happen? For all regular languages, what should happen? There exists a magical number. Yes or no? There exists a magical number. So for all regular languages, there exists a magical number such that what should happen? Such that if, okay, if W, so basically for all W which belongs to L and whose length is greater than or equal to P, for all such W, what should happen? Tell me. See, for all regular languages, there exists a magical number. There exists a magical number such that for all these type of strings, what should happen? There exists XYZ. There exists XYZ. Yes or no? There exists XYZ. Correct? There exists XYZ. Such that W is equal to XYZ and Y is greater than Y is not empty. Basically, I can say Y is not empty and XY length is less than or equal to P and XY power I Z belongs to L for all I. This is your definition using first order logic. Is it clear to everyone? This is your definition, basically a statement. For every regular language, okay, for every regular language, there exists a magical number such that for all these type of strings, for all these type of candidate strings, for all of them, there exists a partition. Remember, there exists a partition. There exists a partition. There exists a partition. Okay, such that W equal to XYZ. In this partition, there exists a partition. In this partition, Y is not empty and XY is within the first P symbols. So this Y is within the first P symbols and you can repeat this Y any number of times. The result should belong to L. The result should belong to L. Okay. So now let me take this example. Okay, consider this language 0 plus 1 plus. Consider this language. Is it regular? Do you know this is regular? Is it regular? Okay, you know this is regular, right? This is regular. We have already seen, we have already created DFA for this. DFA, NFA you can create, and this is actually regular expression. So actually this is itself is regular expression. You know this is regular expression. So this is regular. Okay. Now what some student is doing. Let's see what student M is doing. Student M's argument. Okay, let's check it. Let's check his argument. What he does, assume this is regular. Okay, he is assuming this is regular. Okay, so now, assume this is regular. Now what he is doing, assume L regular. Okay, see, student M doesn't know whether it is regular or not. Student M doesn't know. Okay, he just want to check. So assume L is regular. Then it means there exists a magical number, yes or no? There exists a magical number. So there exists a magical number. Now what this student M is doing, if there exists a magical number, then this string should be able to pump, yes or no? 0 power. So okay, what student M is doing, there exists a magical number. So for all W, so if he is taking this W, what W he is taking? W 0 1 power P. Should this be able to pump? Yes or no? Yes, this is a candidate string, yes or no? Correct. This is a candidate string because W belongs to L, and you can notice the length of W is greater than or equal to P. So this is a candidate string. Okay. Now you can notice what this student M is doing. He is saying that this string should be able to pump. So what he is doing like this: 0 1 1 1 1 1 1 1. Now he is taking this as y. He is taking this as y, and he is taking this as x as epsilon, and he is taking this as z. Okay, he is taking this. This is what student M is doing. Student M is doing like this. Okay, now student M is saying that, tell me, if you repeat y 2 times, if you repeat y 2 times, will it belong? Okay, if you repeat y 0 times, will it belong to x y power 0? Does it belong to L? It doesn't belong to L. Yes or no? It doesn't belong to L, because in L every string should start with 0. Every string should start with 0. Okay, so if you repeat this y 0 times, now you can notice resulting string does not belong to L, so L is not regular. So L not regular. Is this correct logic? So this student has proven that L is not regular. What is the mistake? Tell me, what is the mistake? Of course there is a mistake, right? Of course there is a mistake. What is the mistake? There is no mistake here. You can take this W, no problem. There is no mistake here because you can take this W. This W is candidate string. So there is no mistake. You can take it, no problem. You can take it. But tell me, this should be able to pump. Yes, very good. Tarandeep, very good. Because remember, there exists a split. See this definition. There exists a split. Yes, Sandeep, very good. We can't choose whatever y we want. There exists a y. Okay, so the mistake is here. The mistake is here. This y is not working. Some other y will work. Yes or no? This y is not working. Some other y will work. This is the point. Because remember, there exists a partition. There exists a split. Okay. So what you will tell to this y, to this student M? So this argument is not correct. Not correct argument of student M. And what you will tell this student M? You will tell this student M, see, okay, what you will do? You will tell him that your y didn't work. Your y didn't work. That doesn't mean no y will work. Yes or no? Your y didn't work. That doesn't mean no y will work. Now you can notice this y will work. Can anyone give me y which will work? Can anyone give me y which will work? Anyone? Which will work? This will work. This is your y, this is your x, and this is your z. So this y will work. Correct? Yes or no? You can notice this will work. Now you can notice x, y power I, z, that belongs to L. Is it clear to everyone? So what is wrong with student M's approach? His y did not work. That doesn't mean no y will work. This y will work. Is it clear to everyone? So tell me, all the concepts where you can make mistake, I have told you. Remember this definition, very simple definition. For every regular language, there exists a magical number. Okay, there exists a magical number such that every candidate string, there exists a split, there exists a y, there exists a y. For every string, there exists a y. Okay, so let's come back to this language. Can anyone tell me what is the minimum pumping length for this language? Okay, this is the question. What is the, tell me, will this is pumping length? Which is a pumping length? Which is a pumping length? Okay, some options I am giving you: 10, 20, 100, 1000, 5. Which is a pumping length? Tell me. Which is a pumping length? I am asking pumping length. Yes, this is also pumping length. This is also pumping length. This is also. Why? Why? Because if you make the DFA, I told you, because if you make the DFA, okay, you make the DFA, this is your DFA. In DFA, you have 4 states. Yes or no? In DFA, you have 4 states. In DFA, you have 4 states. In minimal DFA, we have 4 states. 4 states. So because in minimal DFA, okay, for L, in minimal DFA, we have 4 states. So every number greater than equal to 4 is magical number. Yes or no? Every number greater than equal to 4 is magical number, correct or not? So every number greater than equal to 4 is magical number, yes or no? From the proof this comes. But does it mean that minimum pumping number is, I told you pumping length. Okay, this is a pumping length, okay, this is pumping length, okay, this is pumping length, okay, this is okay, this is okay. But let's find the minimum pumping length. For this language, now let's find minimum pumping length. Minimum pumping length. Find minimum. I want minimum. Find minimum pumping length. Let's check it out. Okay, just wait. Let's check it out. This is your language. Your language is 01, 001, 011, like this. Yes or no? Like this. Correct? Tell me, will this work? P equal to 1. Will it work? Will this work? No. Why this will not work? Why this will not work? Because if you take any string whose length is greater than this and you repeat this 0 times, see, if you take any string whose length, you can notice this is a candidate string, W belongs to L, and you can notice length of W is greater than equal to P. So, forget about repeating sequence, forget about DFA. This is what I'm saying, and many times I told you, the minimum pumping length does not depend on DFA. It is a property of language. Minimum pumping length, that is property of language. Forget about repeating sequence, forget about DFA. Okay, so tell me, let's check whether this will work or not. Let's check. Okay, so this is a candidate string or not? Yes, this is a candidate string. Okay, can I pump it? Can I find within the first one symbol? Ananya, P equal to 1. So your Y must be within first one symbol. See, P equal to 1. So Y must be within first one symbol. Y must be within first P symbols. Y must be within first P symbols. So don't make this mistake. Y must be within first one symbol. So what is your Y? The only choice. What is the only choice of Y? This is the only choice of Y. This is the only choice of Y. This is the only choice. Now tell me, if I repeat it 0 times, then fail, yes or no? If I repeat this 0 times, if I do x, y power 0, z, that does not belong to L. So this will not work. P equal to 1 will not work. P equal to 1 will not work. Actually, let me tell you one point. Okay, the one interesting point you can notice one thing. One interesting point you can notice. This is a node. For any regular language, okay, whatever regular language you take, for any regular language, okay, L, for any regular language L, the minimum pumping length, the minimum pumping length. Okay, let's call it MPL. This is not that MPL. Many of you are thinking what's okay, that there is a app MPL. Okay, this is not that. Okay, so what is minimum pumping length? MPL, minimum pumping length. Okay, so you can notice for any regular language, the minimum pumping length should be greater than or equal to length of minimum string of L. Yes or no? Should be greater than or equal to length of minimum string of L. Yes or no? Actually greater than, actually strictly greater than, not equal to, actually strictly greater than. Why? Tell me why. Very easily you can prove it, very easily. Let us assume you have this regular language. You have a regular language L, and in this regular language L, let us assume this is your regular language a power 4 and so on. This is your regular language a power 4, a power 5 and so on. This is your regular language. What the minimum length string here? Tell me. What is the minimum length string here? The minimum length string is 3. Now you can notice P cannot be the minimum pumping length. The minimum pumping length, you can notice the minimum pumping length, you can notice that should be greater than 3. That has to be greater than 3. Why? Because that has to be greater than 3 because if you take P is less than equal to 3, then A cannot be pumped 0 times. Cannot be pumped 0 times. Yes or no? Cannot be pumped 0 times. So you can notice that minimum pumping length should be greater than, should be strictly greater than the length of minimum string of language. Clear or not? Very simple proof. Extremely simple proof. Yes or no? Because if you take less than this, then this cannot be pumped. This cannot be pumped 0 times. You cannot pump it 0 times. Okay. So this is the point. So now let's see. So do I have to check for P equal to 1 here? Actually, for this language, do I have to check P equal to 1? No. Do I have to check P equal to 2? Do I have to check P equal to 2? No. No need. I told you in this language, the P for this language, okay, 0 plus 1 plus, if you see for this language, you see the minimum pumping length, you can notice the minimum pumping length should be greater than this. Should be greater than this. Okay. Minimum pumping length should be greater than or equal to 3. Should be. And now let's check 3. I am not saying that 3 will work. I am not saying 3 will work. I am saying let's check for 3. You don't have to check for 2. Okay, you don't have to check for 2. Actually, so I should say the minimum pumping length that cannot be less than, actually I can say that minimum pumping length cannot be less than. Yes, this is correct. This is more correct. That minimum pumping length cannot be less than equal to this. Yes or no? So let's check whether P equal to 3 will work or not. Check for P equal to 3. It will work or not? Will it work? I know 4 will work. Yes or no? How do I know? How do I know 4 will work? Tell me. I know 4 will work because DFA has 4 states. Because minimal DFA has 4 states. So 4 will work. Now let me check P equal to 3 will work or not. Will it work? Will it work? Tell me. 4 will work or not? P equal to 3, it will work or not? So you can notice this will work. 0 plus 1 plus, you can notice P equal to 3, it will work. Tell me how it will work. Actually, within first 3 symbols, you must have Y, remember. Ame, you cannot give me specific string. Not for a specific string. For all string, you must say within first 3 symbols you must have y. You must have y. Within first 3 symbols you must have y. Now I am saying that this will definitely work. Let me tell it why. Okay. Let me tell you why. Very simple, very simple, very simple. Okay, very simple proof is coming. Actually, whatever string you take, okay, whatever w you take, for all w belonging to L whose length is greater than equal to 3, within first 3 symbols you must have y. And the proof is very simple idea. Tell me, in this language, within first 3 symbols, at least 0 or 1 should repeat, yes or no? At least 2 0 or at least 2 1 I should get, yes or no? For this language, if you see any string of length 3, if you see any string of length greater than equal to 3, any string of length greater than equal to 3, what should happen? Tell me. For all w whose length is greater than equal to 3, okay, for all w at within first 3 symbols, I can say within first 3 symbols, either we have 2 zeros, either we have 2 zeros, or we have 2 ones. Yes or no? Correct? Either we have 2 zeros or we have 2 ones. For example, you can take this string. You can take this string. Here, within the first 3 symbols, I have at least 2 zeros. Or you can take this string. Within the first 3 symbols, I have at least 2 ones. Or you can take this string. Within the first 3 symbols, I have at least 2 zeros. So now are you getting what I am saying? Now are you getting what I am saying? I am saying that, yes, take the second symbol. Take the second symbol. Okay, just take, okay. Here you can take the second symbol as y. Here you can take the second symbol as y. Here you can take the second symbol as y. So just take the second symbol as y. Yes or no? So basically, whatever string you take, just take second symbol as y. So just take second symbol as y. It will work. Yes or no? Tell me yes or no. Second symbol, you can take whatever string you take, just take this second symbol as y. Just take it as y. Just take this as y. So p equal to 3 will work, yes? So for this language, 0 plus 1 plus, for this language, minimum pumping length is 3. And pumping length is greater than equal to 3. Pumping length is basically any number greater than equal to 3, because this is minimum. This is minimum. So pumping length is 3 also, 4 also, 5 also, 6 also, okay, 100 also, 1000 also, 10,000 also, and so on. Yes or no? This is the minimum pumping length. Is this clear to everyone? So can I write some properties? Okay. So let's take before going to break, let's write down some properties that you have understood. Okay, let's write down them. So some important properties of pumping lemma. You will not find them anywhere actually. Maybe on GATEOverflow in my answers you will find these properties, but let's write down some properties of pumping length. Properties of pumping length for regular languages. If you have regular language, then you will have pumping length, yes or no? Basically, okay, for regular languages, let's assume you already know regular language, okay. In the GATE exam, they give you language, just assume. In the GATE exam, they give you language. Can you find it is regular or not? Using Myhill-Lenard theorem, you can find. Yesterday we have done this. You don't need pumping lemma, yes or no? You, from GATE exam point of view, you don't need pumping lemma to prove non-regularity. In the GATE exam, if you apply pumping lemma to prove non-regular, it will take a lot of time, yes or no? So don't apply pumping lemma in GATE exam for proving non-regularity. You can apply our method that we have seen yesterday. In the Mahil-Nerod theorem, I told you direct method. Just by looking at the language, you can find whether it is regular or not. Okay. Just by looking at the language. Okay. I told you the formal method also. Formal proof using Mahil-Nerod theorem, I told you. Okay. So in the GATE exam, to prove whether a language is regular or not, you have to apply them. Don't apply pumping lemma. It will take a lot of time. Okay. Also, but in the GATE exam, what they can ask you, tell me. They can give you regular language. They will give you regular language and they will ask you what is the minimum pumping length. Yes or no? They can give you regular language and they can ask you what is the minimum pumping length. So this is what I am talking about. If you already know language is regular, if you already know language is regular, just by looking at it, you have language, look at it. If you know, okay, it is regular, then you can apply these properties of pumping length of regular language. So what is the first property? The first property, you already know. If minimal DFA of L has n states, then what can you say? If minimal DFA of L has n states, then what can I say? Tell me. Then I can say that minimum pumping length is what? Tell me, minimum pumping length. What can I say about minimum pumping length? Yes, very good. Then minimum pumping length is less than equal to n. And every number greater than equal to n is pumping length. And every number greater than or equal to, every number greater than or equal to n is pumping length. Yes or no? But the minimum pumping length is minimum pumping length that is less than equal to n. Okay, I don't know how much, but less than equal to n. What is the second property? If minimum length string, this property we have seen. If minimum length string of L has length L, then what can you say? Basically, if minimum length string of L, then I can say minimum pumping length cannot be less than or equal to n. Or I can say that minimum pumping length is definitely more than L. So your minimum pumping length is more than L. I don't know how much, but more than L. Correct? Correct or not? More than L. It cannot be less than or equal to L. Correct or not? So these two properties you have done. If you know 100 is pumping length, then automatically, if you know 100 is pumping length, then what it means? If P is pumping length, if you already know P is pumping length, then so is P plus 1, P plus 2, and so on. Yes or no? Any number greater than P is also pumping length. Correct or not? Yes. Any number greater than equal to P is a pumping length. Correct? So this is the point. So these three properties you understood. Third, fourth properties. Okay, so what is the fourth property that I can tell you? Okay, these things will help you when you are checking. So these things will definitely help you. Okay, this is just a guideline. Okay, now let me give you the guidelines. The guidelines are this. First, if you have regular language, let's assume if you already have regular language, you know it is regular language. Let's assume you already know it is regular language. Then what guideline I can give you? Of course, these guidelines I can give you. Okay, these guidelines you have, Another guideline is why. Okay, repeating why. Okay, this is the first guideline. If checking for, let's assume p equal to 10. Let's assume. Okay, if checking for, assume 10. If checking for p, let p equal to 10. Okay, if you are checking for p, then remember your y is within p symbols. Yes or no? Your y is within first 10 symbols. Correct or not? Within first p, or I can say 10 within first 10 symbols. Your y must be within first 10 symbols. Y must be non-empty. Correct? Y is non-empty. Y you cannot take as empty. Okay? Correct? And if you already have regular language, okay, then actually what I can say that to find y, basically which y will work. So basically, if you already have regular language, then find y which will work. Then find y which will work. Yes or no? Find y which will work. Yes or no? If you already have regular language, then you find y which will work. Correct? And to do that, actually, this will help you. Many times, most of the times, repeating y 0 times will help. Repeating y 0 times or 2 times will help. So this repeating by 0 times, it will help most of the time. Okay, in most of the situations, it will help. Is it clear? So this is the point. So let's take some, okay, some regular languages we will take, but okay, let me take some regular languages, and for those regular languages, let's prove. Then after that, we will come back to non-regular languages. Just let me, okay, let's take a break now. After the break, we will continue. Okay, let's take a little bit long break so that you can eat some food. Pumping lemma we will finish. Sana, we will finish pumping lemma. Ashish, we will finish pumping. Hi everyone, welcome back. Okay, so now let me discuss few things. Okay, so read this question and tell me what is this valid proof? Okay, read this. Is it valid proof? Where is the mistake? Or is there no mistake? Let's read this. There is a person, there is a student who is giving this incorrect argument. Okay, so for proving that this language is not regular. So there is a student who want to prove that this language is not regular. Okay, what this student is saying, I will prove L is not regular by finding a string in the language which can be pumped so that resulting string is not in L. Okay, so this is good, no problem. Yes or no? Yes or no? Basically, he want to prove that resulting string is not in L. Correct? Okay. Now what he is doing? He is taking p is less than equal to 3. Okay, this p he is taking, and then he is taking this string, and now he is taking that whatever partition you take, basically, okay, you can notice this is not in L. So L is not regular. Can anyone tell me where is the mistake? Is there any mistake in this argument? Is there any mistake? Where is the mistake? Yes, very good, Sandeep. Very good, excellent. Because this is the mistake. Actually, this is the mistake here. The mistake is this. Because this proof, okay, fine. This proof is okay for p less than equal to 3. So what you can say, this is the mistake. Why this is the mistake? Tell me. Why this is the mistake? Because there exists, you remember, because pumping lemma says, okay, pumping lemma says there exists a magical number. So pumping lemma says that for L, for regular language L, there exists a magical number. But we don't know what is this magical number. See, there exists a magical number. Okay. Now you can notice this student, he has proved, okay, this student has proved that p less than equal to 3 will not work. Yes or no? Let's call this person p. Let's call this person, the name of the person, let's call it M. Okay, let's call this person M. Okay, so this person M, what he has proven? The person M has proven that p less than equal to 3 will not work. Yes or no? Will not work. But it doesn't mean, yes or no? Are you getting the mistake? This person M has proven that p less than equal to 3 will not work. Okay, p less than equal to 3 will not work. But it doesn't mean that no p will work. No p will work. It doesn't mean, yes or no? What this person should do, tell me. Actually, what should be done? What should be done? So this should be done actually. You take any p. Take p. Don't take any specific value of p. No. Don't take p equal to 10, p equal to 20. Don't take p equal to 1000. No. Take p. And now show that whatever p you take, yes or no? Whatever p we take, then which string cannot be pumped? Whatever p we take, 0 power p, 1 power p is counterexample. Yes or no? So this is the simple point. This is the mistake. Are you understanding the mistake here? In this argument, in which line there is a mistake? For example, this question comes in GATE exam or in TIFR exam. If they give you this question and they ask you in which line there is a mistake, A, B, C, D, in which line there is a mistake? So the mistake is in the line B. Yes or no? The mistake is in line B, because this person is proving for p less than equal to 3. Okay, that is fine. That is good. No problem. But it doesn't mean that no P will work. Now, what should be done? Whatever P you take, this is counterexample. For example, if you take P equal to 3, this is counterexample. Yes or no? This is counterexample. This is counterexample. Correct? If you take P equal to 100, this is counterexample. If you take P equal to 10000 10,000, then this is the counterexample. So whatever P you take, we have counterexample. Yes or no? So no P works. So I can say no P works. So non-regular. Correct or not? Now are you understanding pumping lemma? Every small detail you can see. Now let's check this argument. Where is the mistake? In this argument, is there any mistake? And in which line we have mistake? Read this. Assume that the person in the previous, this person M, again this person M is coming. Okay, this person M in the previous question is very stubborn. Okay, now claims to have yet another proof of non-regularity of L. I will prove that L is not regular by finding a string in the language which should be pumped so that resulting string is not in L. Okay, now hence let P greater than 0. Okay, that is good. No problem here. No problem here. Yes or no? There is no problem here. No problem. No mistake. No mistake here. Let P greater than 0. Pick a string S from this. Okay, of at least P. There is no problem here also. Pick a string from the language. Pick a string from the language of length at least P. Again, there is no mistake. He is taking the candidate. Again, there is no mistake. No mistake. Now, then partition S into XYZ such that length of XY is less than P. Okay. XY is, this is the mistake. Yes or no? Are you getting the mistake? Can you notice this is the mistake? This is also the mistake. This is also the mistake. This is also the mistake. So this is the mistake. Why this is the mistake? Because he is taking particular Y. And this is also a mistake. Yes or no? Tell me yes or no. These are the mistake. Can you see? These two are the mistake. This is the mistake. This is the mistake. So what is the mistake here? I can say that mistake. Mistake is taking particular Y. And saying it doesn't work. Do you remember this line I told you? If your Y doesn't work, it doesn't mean any Y will not work. Yes or no? Do you remember this line I told you? Okay. If your Y is not working, then it doesn't mean no Y will work. Yes or no? It doesn't mean that no Y will work. Because pumping lemma says there exists a Y will work. Yes or no? Yes or no? There exists a Y which will work. No, but see, this is the mistake because length of XY should be less than equal to N. He is taking XY as 0 power N. That is the mistake. Are you getting? Okay. Mistake is taking particular XY and saying it doesn't work. If your XY is not working, it doesn't mean that no XY will work. Are you getting my point? The mistake he is doing is actually he should prove that whatever XY you take within the first n symbols, what should be done? Are you getting my point? So what should be done? this should be done that whatever xy you take within the first p symbol, you should prove that whatever xy we take in first p, in first he is taking, okay, in first p symbols, zero power n. Wait. So he is not taking p. Okay, so I think actually here, okay, I think, okay, actually I think this n is not mentioned. What is this n? This n is not mentioned, but the point is this n is not mentioned. If n, actually if this n should be mentioned, that this n is greater than n, greater than 1, at least p, yes or no? Are you getting my point? Actually, okay, in this you should be able to prove that whatever xy we take in first p symbols, that will not work. Yeah, I think this n is confusing actually. This n is confusing. Okay. So if this n is like this, if this n is like this, then there is no problem. Yes or no? Yes or no? Where it is mentioned? No, this is language, Digvijay. This is language. Okay. This n has nothing to do with this n. Digvijay, this n has nothing to do with this n. This is language. I think this should be mentioned that n is greater than equal to 1, less than equal to p. Okay. If this should be mentioned, this should be mentioned. Correct or not? This should be mentioned. Okay. Anyway, this is also a mistake, because you can notice this is also a mistake. So I think there is something confusion here, because I think this n here should be n greater than equal to 1, less than equal to p. Is it correct? You understood the concept, like, okay, there is something confusion here, but you understood the concept, yes or no? This is the concept. Just because some particular xy is not working, if some particular xy is not working, it doesn't mean that no xy will work. Okay, some xy may work. Correct? Okay, so this is the point. So actually, yeah, let me write it. Okay, so this, you consider this as p. Just consider this as p, 0 power p. Yeah, now you can see this is a mistake, yes or no? Just change it, 0 power p. Now this is a mistake, correct or not? There is no by default. Okay, so this is the point. Let's see minimum pumping length. So we have already seen the minimum pumping length concept. Let's find out the minimum pumping length of this. Okay, so tell me. Okay, just wait. I will take, don't worry, I will take all your doubts. But what is the minimum pumping length of this language? For this language, what is the minimum pumping length? Can you notice for this language, what can you say about minimum pumping length? Okay, just by looking at it, I can say that minimum pumping length is definitely greater than 1. I can say this is definitely greater than 1. Okay, definitely greater than 1. Yes or no? Okay, and you can notice in the DFA how many states we have. In the DFA, how many states we have? 3 states. So we have 3 states. So you can say pumping length greater than equal to 3 will work. Yes or no? It will definitely work. Correct or not? Now what we have to check? We only have to check 2. Yes or no? P equal to 2 we have to check. Let's check P equal to 2. Check P equal to 2. Let us check this. P equal to 2. Will it work? Yes, P equal to 2 will work. Correct? Because how can you say P equal to 2 will work? Will work. because you can take the second symbol, yes or no? Will work because we can take the second symbol, because we can take, because y can be second symbol. Okay, so whatever string you take, okay, whatever string you take, this is your y. Whatever string you take, this you can take as y. This you can take as y, because within first two symbols, can I take this as y? Can I take this as y? No, because within first two symbols, so you can take this as y. Correct? Like this. Okay, for this language, what is the minimum pumping length? 0, 0, 0, 1 star. Let us say take this. Just by looking at it, what can you say? What should be the minimum pumping length? You can notice that minimum pumping length should be greater than or equal to 4. Definitely should be greater than or equal to 4. In the DFA, how many states you will have? The minimal DFA of L, how many states? Number of states. What is that? Number of states. That will be 5. Okay. So 1 from here, 1, 2, 3, 4, and 5. Yes. So now what I have to check? So pumping length greater than equal to 5 will work. No problem, will work. So what you have to check? You only have to check 4. Yes or no? Just check P equal to 4. This you have to check. Let us check. Will it work? P equal to 4. Will it work? Yes, it will work, right? Will work. Why? Why it will work? Because you can take the fourth symbol as y. Yes, very good. Y can be fourth symbol. So whatever string you take, you can take this as y. Whatever string you take, you can take this as y. That's it. Yes or no? It will work. No problem. Correct? Okay. So tell me, for this language, 0, 0, 0, 1 plus. For this language, tell me, what can you say about minimum pumping length? That is definitely greater than equal to 5. Yes or no? That is definitely greater than equal to 5. And how many states in the DFA? If you make the DFA, how many states? 0, 0, 0, 1. Any number of 1. So basically total 6 states will be there. There will be a dead state also. So there will be 6 states. So in the minimal DFA, you have 6 states. So what you have to check? So of course, any number greater than equal to 6 will work. Will work. No problem. No problem. So any number greater than equal to 6 is a pumping length. So what I have to check? So I have to check 5. Okay, I only have to check 5. Let's check it. Check P equal to 5. Will it work? Will it work? Again, it will work. Yes or no? It will work. It will work. Because what you can do? Y is equal to 5th symbol. Yes or no? Take Y as 5th symbol. Or 4th symbol. No, or 4th symbol will also work. No problem, basically. Okay. For example, 0, 0, 0, 1, 1. Can I take Y as 4th symbol? Will it work? If I take Y as 4th symbol, no problem, right? Because Y should be within first 5 symbol. Y should be within first 5 symbol. Y should be within 5. Within first 5. Y should be within first 5 symbols. So you can do no problem. You can take this as Y, no problem. Whatever string you have, you can take this as Y. No problem, you can take. Correct? 5th symbol will also work, no problem. Let us take this language 0 star 1 star. What can you say? This for this language, what can you say immediately? What is the minimum pumping length? I can say that yes, minimum pumping length should be definitely greater than equal to 1. And in the DFA, how many states? There is at least one Y we are looking for. 1 1 will not work. Okay, 1 1 will not work because for this string 1 1 will not work. For this string it will work. For this string this will work. For this string this can work. For this string this can work. Is it clear? For different strings you can have different Y, no problem. For different strings you can have different Y, no problem. So tell me here, in the minimal DFA, how many states we have? We have 3 states, right? We have 3 states. So any number greater than equal to 3 is a pumping length. Yes or no? So what you have to check? You have to check 1, 2. You have to check 1, 2. From where you will start? You will start from 1. Yes, of course. You start from 1. Any number. So any number more than or equal to 3 is pumping length. So tell me, will it work? P equal to 1, will it work? Will this work? Will this work? Yes, this will work, right? Yes, this will work because you can notice whatever string you take, whatever string of L whose length is greater than equal to 1 you take, whose length is greater than equal to 1 you take. Okay, for example, you take this string. For this string, what is X, what is Y? For this string, you can notice this is Y. So you can repeat it any number of times, yes or no? And no problem if you repeat it any number of times. 0 star belongs to L. If you take this, then this is your Y. And you know, you can repeat it, this belongs to L. Whatever string you take, whatever. Okay, for example, if you have this string you take, or this string you take, or whatever string you take, then what you can do, tell me. You can take the first symbol, yes or no? You can take the first symbol, correct or not? In any W, Y is equal to first symbol. You can take the first symbol as Y. Yes? Max P, that is enough. Yes, Hare Krishna, we have proven it. We have already proved that within the first, okay, in the proof we have already seen, but within the first P symbols you will have Y. Within the first P symbols. So P equal to 1 will work, yes or no? Everyone tell me, P equal to 1 will work because you can take the first symbol as Y. Whatever string you have, just take as first symbol. For example, if you have this string, take this as Y. If you have this string, take this as Y. If you have this string, take this as Y. Correct or not? You can notice all of them. If you repeat them any number of times, they will belong to all of them. For all of them, you can notice this will belong to L. Yes or no? Is it clear? For this language, what is the pumping length? What is the minimum pumping length for this language? Yes, 1. Actually, you can very easily see this. For this minimum pumping length is 1. Correct? For this language, what is the pumping length? For this language, what is the pumping length? Understand the definition. Okay, this is answer is minimum pumping length is 1. Now let me tell you why. Okay, why? Now let me tell you, just wait. So let me tell you why. Okay, pumping length for finite languages. Pumping length for finite languages. Just understand the definition. Do you remember the definition of pumping lemma? The definition of pumping lemma, do you remember? The definition of pumping lemma. What is that? Pumping lemma. The definition of pumping lemma. In that, do you remember? We have, okay, you can notice that this is like for all regular languages. For all regular languages, okay, there exists a magical number. There exists a magical number. There exists a magical number. Okay, there exists a magical number such that if you have a string, if W belongs to L, such that its length is okay. If this is true, then it can be pumped. Yes or no? If this is true, then it can be pumped. Correct or not? So basically, L is regular. If you have L is regular, then there exists a pump. There exists a magical number. There exists a magical number such that if W belongs to L and length of W is greater than equal to P. If this happens, remember this is if and okay, this is if on okay. This is one way. If this type of strings you have, then for this type of strings, this should happen. Yes or no? Yes or no? Tell me, yes or no? In this language, for all the candidate strings, this should happen, correct? For all the candidate strings, this should happen. So this is one way. This is P implies Q. This is P implies Q. Now tell me, this is if P is false. If P is false, then this whole thing is true. Yes or no? Then this whole thing is true. Correct? Correct or not? So you can notice that if you have finite language, let's assume you have finite language A, comma A, B, B. You can notice that P equal to 4 will work. Why? You can notice P equal to 4 will work. Why? Because there is no candidate string. If there is no candidate string, then there is no problem. Yes or no? If there is no candidate string, then there is no problem. Pumping lemma is satisfied. Are you understanding this? Because if this is true, then whole thing is true. If this is false, if there is no, okay, see, if there is this type of string, if there is any string, then it can be pumped. But if there is no string, for example, P equal to 4 will work, correct or not? It will work. Why? Why it will work? Because there is no candidate string. There is no one to make false. Yes or no? Because now there is no one. There is no candidate string. There is no candidate string to make to become a counterexample. To become a counterexample. Yes or no? To become a counterexample. That's it. Tell me, P equal to 3 will work or not? For this language, will P equal to 3 work? Will P equal to 3 work? The answer is no. The answer is clearly no. P equal to 3 will not work. Because if you check P equal to 3, then this string should be pumped. Yes or no? Then this should be pumped. Now this is counterexample. Yes or no? This is counterexample. Correct? Yes or no? Correct or not? Because now you cannot repeat it 2 times, 3 times, 4 times. There is why, Namrita. See, this is if and only if. Okay, the statement you understand in the definition is if and only if. Okay, sorry, the definition is if only, like one way. The statement is like, the definition is like this. If you see the definition of pumping lemma is like this. it is like this. If L is regular, implies, remember this is if, okay, this is the definition. If L is regular, then implies there exists a P. There exists a P. Implies for all W, if, this is the point. Okay, now you can notice implies for all W, I can say for all W. Let me write it here. For all W, if it's like this, if W belongs to L and length of W is greater than or equal to P, if this happens, then there exists X, Y, Z, and the whole story. Yes or no? And the whole story, correct or not? If this happens for the candidate strings, this will happen. For the candidate string, we must have Y, correct? Namrata, is it clear? For the candidate string, if you have candidate string, then you must have X, Y, Z. Then you must have Y. So that is the reason. That is the reason P equal to 3 will not work. Correct? P equal to 3 will not work. So I can say for finite language, so what is the result you can say? For the finite language, what is the result you can say finally? So for finite language, yes, Amen. So for finite language, what can I say about minimum pumping length? Minimum pumping length is greater than, minimum pumping length is equal to the maximum length string plus 1. Yes or no? The maximum length string plus 1. Correct? So when we were writing these notes, okay, some notes we have written here. So there you can write this. Some guidelines and some properties. Yeah, in these properties you can write this. So some properties we have seen. The fourth property, let me write. If L is finite and length of longest string, I can say, okay, length of longest string is K, then what can you say? Then your minimum pumping length is equal to K plus 1. You can very easily say K plus 1. Any number greater than equal to K plus 1 is a pumping length. Correct? Is it clear to everyone? Because there is no counter example, so you can say like this. Okay. 0 star 1 star we have already done. And what about this? Okay, let's take this language. 0 star, there is a language. So before this, let me take another language, some easy language, let me take. So consider this language. A plus B, A star, union, okay, union, B, 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 A plus. Consider this language. Why P is going? Hare Krishna, you can draw DFA, right? Okay, for example, if you have DFA of size of number of states 10, then you can create a DFA of number of states 20, no problem. Hare Krishna, you can put some extra states in the DFA. We have already seen for every regular language we have infinite number of DFAs. You can put unnecessary states, you can put unreachable states, you can put. So tell me what is the minimum pumping length of this? Find minimum pumping length. First you tell me what can you say about minimum pumping length directly, just by looking at this. Just by looking at this language. Look at the language, don't look at part. This is the most, okay, this is the mistake many teachers also do. I have seen many teachers, they do also this mistake. Look at the language. Okay, think about the language, not about a part of the language. Think about complete language. Not about a specific part. Okay, so tell me, what can I say? In this language, the minimum pumping length I can say that is definitely greater than equal to 3. Yes or no? Definitely greater than equal to 3. Because what the minimum in this language, what the minimum length string? What is the minimum length string? That is AB. Look at the language. In this language, the minimum length string is AB. So I have to check. Okay, will 3 work? Let us check. Will it work? P equal to 3. Will it work? Let us check. Will it work or not? Now let's check for these strings. Will it work for this string? Will it work for this string? Will it work for this string? P equal to 3. Will it work? No, it will not work, right? Within the first P symbols, here you must have Y. Yes or no? Yes or no? Within first 3 symbols, you must have Y. Symbols, you must have Y. Correct? You must have Y. Now tell me, if you take any Y, for example, if you take any Y, then at least one B is gone. Yes or no? At least one B is gone. For example, if you take this as Y, then A does not belong. If you take this as Y, correct or not? If you take this as Y, then if you repeat 0 times, then A does not belong, right? So whatever you do, whatever Y you take, this cannot be pumped. This string cannot be pumped, correct? Cannot be pumped. Yes or no? Now let me take P equal to 3. P equal to 4. Will it work? P equal to 4. Will it work? Why it is not working? Tell me. Why it is not working? P equal to 4. Will it work? Again, it doesn't work, right? P equal to 4. You can similarly see this string cannot be pumped. This cannot be pumped. You can just check. You can check it. This cannot be pumped. Whatever you do, this cannot be pumped. This string cannot be pumped. BBB is not a candidate string. P equal to 4. So candidate string must have length greater than equal to 4. BBB is not a candidate string. Vidyasagar, you are looking at a part. See this. Think about the complete language, not about a specific part. You are thinking about this specific part. I know in your mind this specific part is going on. I know. I will give you one example where this problem will be solved. But P equal to 4 will not work, because whatever you do, whatever Y you take, the result will not belong to the resulting string will not belong to L. Will this work? P equal to 5. Will it work? Yes, it will work, right? It will work, because for these strings, what you can do? For these strings, what you can do? You can take for these strings, you can take this as Y, and for these strings, A, For these strings, what you can take? You can take a, what you can take as y for these strings? Tell me. No, you cannot take y as, can you take y as the first a? No, no, no. For example, for this string, what will be your y? Just tell me this point. For this string, what will be your y? For this string, can you take this as y? Can you take this as y? No, this you cannot take as y. But you can take this as y, correct? This you can take as y. Yes or no? This you can take as y. And for this string, what y you will take? For this string, what y you will take? Now you can take this as y, no problem. Yes or no? Correct or not? Is it clear to everyone? Different strings can have different y, no problem. Different strings can have their own y. Different people, they can have their own y. But for every string, we must have y. Yes or no? For every candidate string, we must have y. Different candidate strings can have different y. Is there any problem with this? If you repeat this any number of times, the result still belongs to L. Yes or no, Tandeep? The result still belongs to L. Now let me take this example. Okay, so consider this. Consider this. Okay. Yes, Hari Krishna. Minimum pumping length is always less than or equal to n. All these things we have actually proven. Were you in the class? I think you were not in the class, I think. So if we say p greater than x, so then every string should satisfy that p. Yes, every string should be pumped. I am saying every string should be pumped. Okay, let's check this string. So tell me, will this p equal to 1? P equal to 1, I don't have to check. Yes or no? P equal to 2, I have to check. Okay. P equal to 1, I don't have to check. Let us check p equal to 2. Let us check p equal to 2. Tell me, will it work? Will it work? P equal to 2, will it work? Will it work? P equal to 2. Okay, now tell me p equal to 2. Will it work? This is the language now. This is the language. Will it work? P equal to 2. Will it work? Of course it will work. Of course it will work, right? Whatever string you take, what you can do? What you can do? You can take this as y. You can take this as y. Yes or no? You can take this as y. And the resulting string will belong to L. It will belong to L. It need not belong to the part. It should belong to L. Look at the language. Don't look at the part. Look at the language. Result should belong to language. Result should belong to language. You can notice. Okay, you can notice that actually this is basically same as B star A plus. Correct or not? Can I say they are same? Basically, this is just subset of this. Just to confuse you, actually this is this. This is just to confuse you. Okay, now let us check this language. 0 star 1 plus. So this is your language. 0 star 1 plus 0 plus 1 star union 1 0 star 1. From where should I start checking for minimum pumping length? For minimum pumping length, from where should I start checking? I should start checking from P equal to 3 onwards. Will it work? P equal to 3. Will it work? Will this work? P equal to 3. 101 can be pumped, right? There is no problem with 101. This you can take as Y. There is no problem. This you can take as Y. No problem. You can take this as Y. So will it work? For all these strings, this is working. No problem. For all these strings, this is working. For all these strings, whatever string, you can take this as Y. For all these strings, this is working. For all these strings, is it working? P equal to 3. Is it working? For all these strings, will it work? Will it work? See, okay, will it work for this string 1 and then 0? Will it work for this string 100? Will it work for this string? Yes, it will work, right? Actually, whatever string you take, it will work. From this, okay, whatever string you take. For example, if you take this string which start with 0, if your string is starting with 0, then you can take this as Y, correct? Correct or not? If your string is starting with 0, then you can take this as Y, correct or not? And if your string is starting with 1, if your string has at least 2 ones, then you can take this as Y. If your string has at least 2 ones, then you can take this as Y. If your string is like this, then what you can do, tell me? So for example, if your string is like this, then you can take this as Y, correct? And if your string is like this, 1, 0, 1, and so on, then you can take this as Y. So whatever string you take, you can find Y, yes or no? For every string, you have Y, correct or not? Is it clear? For every string, we have Y. Is this clear to everyone? So this will work. So minimum pumping length is, minimum pumping length is 3. Anyone has any doubt, let me know. I have proved that for every string, this is your language, for every string, you can have Y. Whatever string you have, you can have Y. Whatever string you take, you can have Y. Yes or no? Your Y will work. No, Tarandeep, we cannot do that. Please don't do that. That is the mistake. Now let me tell you why that is the mistake. Because here you can notice that is the mistake. Consider this language. Okay, consider this language. A, B star, C star, union, A power n. Okay, A plus. I can say A plus A plus. Okay. Consider this language. Okay, let's consider this language. Let me consider this language. So A, B power n, C power n, union. Okay, union A, Just wait. Okay, let me take that. Let me take this example. Yeah, take this example. Consider this example. Now consider this example. So first you read this. First you tell me, is this language regular? Look at this language. Is it regular? See, this language is saying that A, B power n, C power n. Means if your string has one A, then this should happen. Or if your string has like not A power 1, like, okay, if your string has, for example, if your string is starting with exactly 1A, if your string is starting with exactly 1A, then this should happen. And if your string is starting with this, then you can have anything. Okay, then you can have anything, basically B plus 1, B plus C whole star. Yes or no? Or you can have B plus C whole star. This is your language, correct or not? Can you understand this language? This language is saying that if string is starting with exactly 1A, then you have B power n and C power n. But if your string is starting with either 0A or at least 2A's, then you can have B plus C whole star. Yes or no? Yes or no? So this is the language. Correct? Is it regular? Is this language regular? This language is not regular. Why this is not regular? This is not regular because if your string is starting with A, you can notice if your string is starting with A, now you have to find how many B's you have seen. Yes or no? Now you have to find how many B's you have seen so that you can see C. Okay. If your first symbol is A, if your string is starting with exactly 1A, then you have to do this infinite possibilities. You have to keep track of infinite possibilities, correct or not? So this we have already seen. So this language, this language is non-regular. But now, will this language satisfy pumping lemma? Okay, tell me, P equal to, okay, for this language, let us check for this language, let me check. P equal to 2 will work or not? Let me check. Will it work? P equal to 2, will it work? Let us check. So your language is this, you can notice. Your language is this, A, B power n, C power n, union, A power m, B plus C whole star, where m is not equal to 1. Okay. Now I am saying that this is Rajan, this is the language. If your string is starting with exactly 1A, then this should happen. If your string is starting with any other number of A, then this should happen. Okay. Now let me check P equal to 2. Will it work? Will it work for these strings? Just tell me. Will this work for these strings? Will it work for these strings? No, W doesn't have A. W doesn't start with A. W doesn't start with A. Okay. W doesn't have A. So let me take W doesn't have A. No problem actually. W doesn't start with A. So for simplicity, let me do this. W doesn't start with A. Sorry, W doesn't have A. Okay, let me do this. Yeah. Now tell me, is it correct now? Now this is correct, right? No problem. Now tell me, will this work for these strings? Yes, this will work for these strings, right? If you are not starting with A, like if you are taking any string of this, okay, if you are taking any string from this, then you can take the first symbol as Y, yes or no? Y you can take as the first symbol. if you are taking strings from this, like from this part, then you can take y as first symbol. This is the point. If you have this string, then what you can take y? Tell me. If you have this string, what y you can take? What y you can take? Tell me. For this string, what y you can take? You can take this as y, yes or no? No, p equal to 2, Tarandeep. Tarandeep, p equal to 2. So within the first two symbols, correct? For this string, you can take this as y. Tell me, for this string, what you can do? Again, you can take this as y. Correct? Again, you can, now you can take this as y, correct? If your string is like this, if your string from this, then you can take y as first symbol, no problem. So all these strings, they can be pumped, yes or no? All these strings, they can be pumped. Now, let me check whether these strings can be pumped or not. Let me check. So, if you take this string, can it be pumped? Can it be pumped? This string, p equal to 2, I am checking p equal to 2. What y I can take? Tell me. What y I can take? I can take this as y, right? I can take this as y because you can notice that if I repeat y equal to 0, if I do y power 0, then you can notice this belongs to language. This belongs to language or not? This BC belongs to language or not? Yes, this BC belongs to language. Hare Krishna, part doesn't matter. Language matters. This is what I am telling you again and again. Look at the language. The result should be in the language. Part doesn't matter. The result should be in the language. So result is in the language. If you do y power 1, then also result is in the language. If you do y power 2, then also result is in the language. Can you see? This y you can take, yes or no? For this string. So for any string, b power n, c power n, for any string, you can take this as y. Correct or not? If you repeat it any number of times, the result will belong to L. Either it will belong here or it will belong here, but the result will belong to L. So can you notice this language L was non-regular, yes or no? This language is non-regular. Can you notice this language is non-regular? So you can notice this language is non-regular, but pumping lemma is satisfied, yes or no? But pumping lemma satisfied. Okay, and pumping length p equal to 2 will work. Correct or not? Is it clear to everyone? So can you notice one point you can notice? Every regular language must satisfy pumping lemma. This is one way, remember. So if you have a regular language, then it must satisfy pumping lemma, yes or no? It must satisfy pumping lemma. Every regular language must satisfy pumping lemma. But this does not mean, if someone is satisfying pumping lemma, that does not mean some non-regular language also satisfy pumping lemma. So this is the point basically. If some language is not satisfy pumping lemma, then what can I say? If L does not satisfy pumping lemma, then what can I say? Tell me. If L does not satisfy pumping lemma, then L is definitely non-regular. Yes or no? Then L is definitely non-regular. Definitely non-regular. Yes, correct. If someone is not satisfying pumping lemma, then it is definitely not regular. But if someone is satisfying pumping lemma, if someone is satisfying pumping lemma, then it may or may not be regular. So can you notice, pumping lemma is used to prove regularity or non-regularity? What can you prove? So these are the points. So pumping lemma we can use to prove, yes, this is used to prove non-regularity. First, used to prove non-regularity. You cannot prove regularity, but you can prove non-regularity. Second, based on pigeonhole principle. Yes or no? We have seen the proof based on pigeonhole principle. The proof is based on pigeonhole principle, correct? Correct. So these are the points. In the Mahil-Nerod we have by implication. Mahil-Nerod is two-way. For this language, what are the, okay, so I think that, yeah, we have enough time actually. W contains 0, 0 as substring. For this language, what is the minimum pumping length? This is your language. What is the pumping length? Minimum pumping length, what is that? You can notice that minimum pumping length should be greater than or equal to 3. And actually P equal to 3 will work. It will work. It will work. Definitely it will work. Whatever string you take, within the first three symbols, you can find, for example, tell me, for this string, what will be your, for this string, is it candidate? Is this string candidate? Yes, this string is candidate for P equal to 3. What should be your P? So this should be your Y. You can take this as Y. Is this candidate? Is this candidate? Is this candidate? No. Is this candidate? Yes, this is candidate. So tell me, what is your Y? You can take this as Y, no problem. You can take this as Y. And for this string, what will be your, for this string, what is the Y? For this string, what is your Y? This is your Y. For this string, what is your Y? This is your Y. So for every string, you can have Y, yes or no? Every string can be pumped. Every candidate string can be pumped. Clear? For this language, what is the a power n such that n is less than equal to 100? What is the pumping length? What is the pumping length for this language? Yes, that is 101. Because this is finite language. You can notice this is only finite language. Okay. For this string, for this language, a power n, b power n, so that n is less than equal to 1000. What is the minimum pumping length? Is it regular? Is this language regular? Is this language regular? Yes, because it is finite language. You can notice this is finite language. Every finite language is regular. Every finite language is regular, yes or no? Every finite language is regular. How can you prove it? How can you prove it? Every finite language is regular. What is the proof? Because if you have finite language, okay, then you can write regular expression, yes or no? Then you can write regular expression. You can very simply write regular expression. This is your regular expression. If you have finite language, if your language is finite, then this is your regular expression. This is your NFA. This is your NFA. Correct? So every finite language is regular. So this is a finite language. What is the minimum pumping length? MPL. Minimum pumping length. What is that? That is 2000 G. Okay, this is 10,000. So 20,001. That is 20,001. Okay, so actually everything we have seen in the pumping lemma. Okay, so let me just take 1-2 example just for your practice sake. For this language, just for practice, 0 power, let's assume a power m, b power n, m is greater than n. Tell me how will you prove that this is non-regular? We have already seen in last class that this is non-regular. This is non-regular, right? We have already seen this is non-regular. But let's prove it using pumping lemma. So assume it is regular. Assume L regular. What it means? It means there exists a magical number. There exists a P. It means there exists a magical number. Now, I am saying that whatever P you take, this string cannot be pumped. Whatever P, this string, which string cannot be pumped? Whatever P you take, I am saying this string cannot be pumped. This string cannot be pumped. Is this candidate string? First you tell me. Is this string candidate? Yes, it belongs to language. Also its length. You can notice. This string is candidate. This is candidate because W belongs to L and length of W is greater than or equal to P. So tell me, whatever P you take, I am saying that whatever P you take, this cannot be pumped. Can you tell me why? This cannot be pumped. This cannot be pumped. Why? Tell me why. Because Y must be where? Tell me, where must be Y? Y must be within first P symbols, yes or no? Y must be within first P symbols. So you can notice Y must be here. First P symbols. Within first P symbols. We must have Y. Now tell me, it means Y must have at least one A. Yes or no? It means Y must have at least one A. So if we remove Y, if we repeat Y 0 times, then what it means? Then definitely this string you will get. Then resulting string is this. Then resulting string will be A power K, B power P, where K is definitely less than or equal to P. Yes or no? Because at least one will be gone. See, at least one A will be gone. At least one A. I can say at least one A will be gone. When you repeat Y 0 times, then it means at least one A is gone. At least one A gone. If at least one A gone, then I can say that this type of resulting string we will get where K is where K. So this does not belong. Yes or no? So this this string, this resulting string does not belong to L. So whatever y you take, you can notice whatever p you take in this string, whatever y you take. So it's like this. Whatever p you take, for this string, whatever y you take, the resulting string does not belong to, I can say, when you do this, that does not belong to L. Correct or not? Is it clear to everyone? So non-regular. Because pumping lemma is not satisfied. Yes or no? So pumping lemma is not satisfied. We don't have magical number. Can I say we don't have magical number? Yes or no? There is no magical number for this language. For this language, there is no magical number. I can say this language does not satisfy pumping lemma. Correct or not? Is it clear? A lot of examples we have taken. Okay, some languages I am writing. You quickly tell me the counter example string. Okay, some non-regular languages I am writing. And you give me the counter string. Okay, which string will be counter string? Candidate counter string, basically. Candidate counter string. Okay, so for this language, what counter string will work? For this language, you can notice this counter string will work. Yes or no? A power p, b power p. This will work. For this language, what counter string will work? Again, the same will work, right? Again, same will work. No problem. For this language, what counter string will work? Think and tell me what counter string will work. Give me any one counter string. Yes, very good. No. This will not work. See, this will not work. A power p. This will not work. A power p, b power p plus 1. This can be pumped. Oh, no. Actually, this, if you repeat many times, then this also will go out of. Yes, this is counter string. But this will not work when you do. See, how can you prove? Okay, let me do. Okay, see, this will work. No problem. This will work. But okay, tell me when it will work. When you repeat y, how many times? Can you repeat y 0 times? Yes, but you can repeat y many times. Yes or no? You can repeat y many times. So you can notice this language. Okay, let me take this language. A power n, b power m, where n is less than equal to m. For this state, for this language, this will work. No problem. A power p, b power p plus 1. This will be counter example. Why? This will be counter example. Because whatever y you take, we take, if you repeat it p times, then tell me what will happen. If you repeat 2p times, yes or no? Are you getting my point? Whatever y you take. So for example, this is your string a power p, b power p plus 1. So these are p symbols and these are p plus 1. Now whatever y you take here, if you repeat this y 2, okay, tell me, if you repeat this y 2 power p times, then this will not belong to L. Correct or not? Correct? If you repeat it too many times, okay, you are repeating. Too many times you are repeating. If you repeat it 2p times, then I can say the resulting string does not belong to the language. Correct or not? 2 is not enough. Yeah, 2 is also enough, I think. Yes, 2 is also enough. Yes, I think 2 is also enough. If you repeat 2 times, then that is also enough. Very good. Yeah, actually 2 is also enough. So for this, a power p, b power p plus 1, if whatever y you take, 2 is also enough. Y we take x y power 2 z does not belong to L. This is also enough. Yes, right. Okay. Because whatever y you take, this is your y. Yes or no? This is your y. So your y has at least one a. Yes or no? Your y has at least one a. Correct? So y has at least one a. Okay, y has at least one a. If you repeat it 2 times, then definitely now your number of a is not less than number of b. Correct? Now your number of a is not less than number of b. So this is fine. And for this language, WW. For this language, which string you will take? For this language, WW. This is non-regular, right? So I'm writing non-regular. Here I am writing non-regular languages. And you tell me what is the counter candidate string. So tell me for this language, what counter string you can take? Tell me. WW. No, assume P. Assume regular, assume. Okay, whenever we have assume P, so at least you must give me answer in terms of P. Like assume you cannot give me A. Yes, Sandeep, very good, excellent. Okay, the counter candidate string that I can take, that is, you can take this A power P, B power P, A power P, B power P. Yes or no? Or you can take this A power P, B, A power P, B. This also you can take. Yes or no? Correct? Can you take this A power P, B power P? Is it candidate string? This is not even candidate string. This is not even candidate string because this does not, okay. This is not, because this does not belong to L. Also, can I take A power P, B power P? Can I take A power P, A power P? Can I take this? This is candidate string, but this will not work. This will not work because you can pump it. Actually, this is candidate string, but this will not work. Let me tell you why. So, for example, this is your language. This is your language. Now, if you take this string A power P, basically A power 2P. Basically, you are taking A power 2P. Okay, this string you are taking, Hare Krishna, right? You are taking this string. Yes, this is candidate string, no problem. This is candidate string, no problem. But this can be pumped. This can be pumped. I can pump it very easily. I can pump it. Let me pump it like this. Just select this. You can pump it. This is your Y. So you can pump it. So this will not work as counter. So this is candidate string, but not counter example. Okay. Is it clear to everyone? So this is counter example. This is also counter example. A power P, B, A power P, B. Okay. So tell me, for this language, W, for this A power N, B power 2N, what will be your counter candidate string? You can take A power P, B power 2P. Yes or no? You can take A power P, B power 2P. And for this language, A power M, B power N, M is not equal to N. For this language, for this language, a power m, b power n, m is not equal to n. M is not equal to n. This string can be pumped, right? A power p, b power p plus 1. This string can be pumped. You can pump it. You can pump it. Yes or no? You can pump it. Correct? You can definitely pump it. See, for this language, you can definitely pump it. No, Sandeep, you cannot choose Y. See, like you are choosing Y. This is the mistake. This you can pump. You can pump it. How can you pump it? How can you pump it? This you can actually pump. You can very easily. This can be pumped. This can be pumped. What you can do? You can take 2 A's. Maybe you can take 3 A's. This can be pumped. You can take 3 A's as Y. Yes or no? You can take Y as this. This you can take as Y. Correct or not? This can be pumped. You can take Y as 3A. So this can be pumped. I can take Y as AAA. So this can be pumped. So can you see whatever string you take, that can be pumped? Like there is counterexample, but that needs some factorial and something. Okay. So in the GATE exam, of course, they will not ask you. There is counterexample. You can create counterexample. Okay, but that is in terms of factorial, like a power p, b power p factorial, something like this. Okay. So this I will share in the group. You can read it, but this is not required. But there is counterexample. Sometimes the counterexample is very hard. For this language, the counterexample is in terms of factorial, something like a power p, b power some p plus 1 something factorial, some factorial something. Okay, like something like this, factorial. So are you getting what I'm saying? Basically, but there is counterexample. For this also we have counterexample. Okay, so you don't have to worry, because there are some languages, let me tell you, there are some languages which if you try to prove using pumping lemma, if you try to find counterexample, that is extremely hard. Okay, so you don't have to worry about them, because in the GATE exam they are not going to they are basically, if they give you a language, just assume they give you a language and they ask you, is it regular or not? So will you use pumping lemma? No, don't use pumping lemma, directly solve. So you can notice in the GATE exam, if they give you a regular language, and they ask you, what is the pumping length? What is the minimum pumping length? That you can solve, right? That you can easily solve. A lot of practice we have done. Correct? So this type of things. So you can notice there is a counterexample, but extremely complicated. I will tell you. There is a counterexample. But counterexample will have some factorial something. So you don't have to worry. Okay. If anyone is curious, you can skip it. But if anyone has curiosity, then you can. Why a power p, b power p is not counterexample? Tell me. A power m, b power n, m is not equal to n. Is this counterexample? Is this counterexample? This is not counterexample, because you can take this as y. Now this is pumped. Now this string can be pumped. You can take this as y. Now this, you cannot take y as 1. You cannot take y as 1. Because if you take y as 1, you pump 2 times, then it will go out of language. Yes or no? Yes or no? If you take this, then x power y to z, that will not belong to L. So you cannot take this, but you can take this A, triple A. Yes or no? Triple A you can take. Now you can repeat it any number of times. Repeat any number of times you repeat, the resulting string will belong to L. So this string can be pumped, yes or no? This can be pumped. Sandeep, is it clear? Okay. For this WWR, what is the counter example? Tell me. For WWR, WW reverse. Give me counter example for this. A power P, B power P, B power P, A power P. Very good. Or you can do A power P, B, B, A power P. This will also work. This will also work. Correct? You can check it out. These will work. Okay, these will work. So like this, can you do like this? You can do basically. Clear? So all the like basic fundamental these languages I have given to you. For this word counter example, you can do A power N, B power N, C power N. So for this counter example will be A power P, B power P, C power P. Now this you can take as counter example. Okay. And for this language, so like this, okay, like this you can write languages and you can find the okay. So like this you can do. Correct or not? Okay. So now are you comfortable with the pumping lemma? Did you understand pumping lemma? This pumping lemma is analytical. Vidyasagar, P is prime, that is little bit complicated, because if you take this A power P, P is prime. For this also we have counter example. Actually, the counter example is you have to repeat. Okay, the counter example is you can take any A power P. Okay, so you can take any A power P, no problem. A power N, N is prime. You can take A power P, but actually this will work as counter example. But how many times you will have to repeat? You will have to repeat Y. You will have to repeat Y. How many times? So you will have to repeat it P plus 1 times. You will have to repeat Y P plus 1 times. Let me show you. Actually. This let me show you. For example, this language you can prove. Okay, this language you have. Your language is A power N, N is prime. I am saying that you can take any. Let's assume assume L is regular. Assume L regular. Okay, so there exists a magical number. Now, if this is your magical number, then tell me, just point, okay, this point you tell me. If this is the magical number, can I assume this magical number is prime number? Can I assume this magical number is prime number? Can I assume? I can assume, right? See, if this magical number is P, then every number greater than this is also prime. Greater than this is also magical. If this is magical, then P plus 1 is also magical, P plus 2 is also magical, P plus 3 is also magical. Yes or no? P plus 1 is magical, P plus 2 is magical. So like this. So can I take this? Let's assume this is prime number. Can I take this as magical? Yes or no? Are you getting my point? See, because if P is magical, then P plus 1 is magical, P plus 2 is magical, P plus 3 is magical. So I can take this, just go like this. So I can take this prime number as magical. Yes or no? I can take this prime number as magical. So without loss of generality, I can assume. Without loss of generality, what I can assume, tell me? We can assume P is prime. Is this clear to everyone? Because if P is magical, then P plus 1 is magical, P plus 2 is magical. You can go like this and you go to a prime number and you take that. You go to a prime number and you take that. So you take the prime number which is magical. Yes or no? Are you understanding what I'm saying? Anyone has any doubt in this? You can take a prime number which is magical. Vidyasagar, I am not talking about, I am talking about there exists a magical number. If P is magical, then P plus 1 is magical, P plus 2 is magical. So I can take a prime number which is magical. Yes or no? Is it not clear to anyone? Is there anyone to whom this is not clear? Very simple observation. There exists a P, so I can just assume that this is prime, no problem. So, okay, now you can notice. So you have basically there exists a P. This is your pumping length. This is your pumping length, or you can say magical number. Magical number. And without loss of generality, I can assume that this is prime, no problem. I can assume this is prime also. I can assume. Now take this string, A power P. Is this candidate? Is this string candidate? A power P. Yes, this is candidate. Because P is prime. Because P is already prime. So this is candidate. Because P is already prime. If this is candidate, now tell me. Just repeat. So you have some Y, yes or no? So this is your string. This is your string. A. Okay. P is prime. So you have some Y. Some Y you have. Tell me what is the length of W? Can I say length of W is, that is length of X plus length of Y plus length of Z? Yes or no? Yes or no? Some Y you have. There exists a Y. Now you repeat this Y P plus 1 times. Let's repeat. Repeat Y P plus 1 times. Then tell me. Then you will get, okay, what will be your length? What string you will get? Tell me. I can repeat Y these many times. Yes or no? I can repeat Y these many times. I can repeat Y these many times. So what string? What is the resulting string? What is the resulting string? The resulting string, you can notice the resulting string is A power K. What is the K? Your K is what? The resulting string is this. X is as it is. Yes or no? X is as it is. Z is as it is. I am repeating Y P plus 1 times. So it means I am repeating Y P plus 1 times. It means Y is as it is and plus P times Y. Yes or no? Like if I repeat Y 2 times, then plus 1 extra Y. So like this, correct? Is this correct? Is this correct or not? Very simple. I am repeating Y P plus 1 times. So finally, what is my resulting string? So my resulting string is A power K, where K is basically W, length of W. K is length of W plus P into length of Y. Plus P into length of Y. And what is length of W? Tell me. What is the length of W? The length of W is P. The length of W is P. So length of W is P. P plus length of Y. What is that? That is P into 1 plus length of Y. This resulting string, this is not prime. Yes or no? This is definitely not prime. So you can notice this resulting string, this is not prime. Correct? Is this clear to everyone? Like, okay. Can you see sometimes this pumping lemma is complicated? Okay. So in the GATE exam, you do not have to apply pumping lemma for non-regular languages. Pumping lemma is used for non-regularity, but you don't have to apply in GATE exam for non-regular languages. Yes or no? Okay. So you can notice pumping lemma is actually For some languages, pumping lemma is really complicated. Whatever y you take, Hare Krishna, whatever y, I did not take any specific y. I did not take any specific y. You can notice there is no specific y I took. Whatever y you take, repeat it p plus 1 times. Is it clear, Hare Krishna? You can take whatever y you take, just repeat it p plus 1 times. This is what I'm saying. Correct? So that's it. So for this language, this will work as counter example, but you repeat y p plus 1 times. Okay. So this is the point. Okay. So this is enough. Let me know if anyone has any doubt. Kindly do not ask, kindly do not keep any doubt. Do not hesitate. Okay. Now pumping lemma is over. Do not hesitate. Just ask any doubt what you want. Okay. Do not hesitate. Whatever doubt you have, just ask. Tell me what your doubt. What is your doubt? Rajan, because I know how to, like, I want to create a counter example, so I'm repeating p plus 1 times. Okay, because I know that repeating p plus 1 times will give me counter example. So I'm repeating p plus 1 times. It doesn't make sense, right? For many languages, I know what should be done. So I will directly do that. See, okay, let me tell you one thing actually. This is an interesting thing. Have you studied stress and algorithm? Stress and algorithm, have you studied? Stress and algorithm. Okay, so this stress and algorithm you have studied, right? In algorithm subject you have studied, correct? For matrix multiplication something. And this recurrence relation you have. Something C, T, something. Okay, what is the recurrence relation? Do you remember? I think something like this. Something like this you have. 7T n by 2 plus, what is that? N by 2. Okay, 7P n by 2. N by 2 or n by 8? I think n by 8. N by 2. Okay, n by 2. And plus n square. Is this stress? So anyway, okay, the point is very simple. Actually, what point I want to make. So in this stress algorithm, you have this recurrence relation. Now, when I was studying, so this recurrence relation you have, and in ISC, when we were studying this, so in ISC, basically, this stress algorithm we were studying. And the one line the professor said that you can prove this stress algorithm if you know the proof. Like, can you see? You can prove stress algorithm if you can prove, basically, you can prove the stress algorithm if you know the proof. It basically means, no. See, Hare Krishna, this is not true for many proofs. A lot of proofs I have proven myself. Actually, okay, I'm not boasting about it, but a lot of proofs you can yourself prove. Yes or no? There are a lot of things you can prove if you understand the fundamental principles. If you understand the concepts, then there are a lot of things you can prove by yourself. Okay, but some things are so unique. Okay, this stress algorithm, this was so unique that you cannot think it by yourself. So this person, this stressor, he thought, okay, he thought by himself. But if you want to think, okay, how to prove this stress algorithm, then actually it is very, 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 very hard, very complicated. So this line the professor said, and this line actually is very correct. Sometimes you can prove if you know the proof. For example, in this a power p, p is prime. Yes or no? A power p, p is prime. I know that if I repeat p plus 1 times, then I will get counterexample. Okay, but if I tell you to think by yourself, then I think it will be a little bit complicated. I am not saying you cannot do it, but it will be complicated. Yes or no? Maybe some time you need, maybe few hours, or maybe after a few days also you cannot think by yourself. Okay, so anyway, don't worry about it. The point is very simple, that for some languages, finding the counterexample string is very hard. So you don't have to worry about it. Okay, so don't find for every string, for every language, don't go and find counterexample string. What I have told you in this lecture, I have covered everything. Whatever you need to know about pumping lemma, that I have told you. Is it clear to everyone? Rajan, is it clear? You don't have to worry about the counterexample string. For some languages, around 9 or 10 languages, the standard non-regular languages, for them you can find the counterexample string. For example, these languages, this is easy, right? For these languages, finding the counterexample, that is easy, correct or not? Finding the counterexample, this is easy. Okay, so now this is the point, so you don't have to worry. Minimum pumping length is a standard thing, can be asked in GATE exam. Actually, it should not be asked in the GATE exam. This should not be asked. Actually, in the GATE exam, asking a pumping lemma question is extremely hard. I don't want to make things complicated, but there is something called generalized pumping lemma. Hare Krishna, there is something called generalized pumping lemma. See, I don't want to make things hard, so that is the reason I am just avoiding it. Okay, but pumping lemma is not standard. There are many pumping lemma statements. Okay, so this pumping lemma that we have studied in our today's class, the pumping lemma that we have studied, this is the most general form of pumping lemma. I am not saying this is the standard. I am saying this is the most general form of pumping lemma. This is what I am saying. The pumping lemma that we have studied. That we have studied is most popular form of pumping lemma, or I can say is most popular, or you can say general is most popular, or I can say generally used pumping. Okay, generally used, most popular form of pumping lemma. Actually, there are many generalized pumping lemma is also there. Okay, so that is the reason, if you see in the GATE exam, only one time question has come. In last 40 years, only one question has come. Why is that? Why is that? Because asking a question from pumping lemma, creating a question from pumping lemma, that is not easy. You have to give the definition of pumping lemma, yes or no? If I want to ask you the question of pumping lemma, then any good question if I want to ask, then I have to give you the definition of pumping lemma which I am using, because maybe I am using some other definition. The pumping lemma definition, that is not standard. There is something called generalized pumping lemma. Okay, there are some things, so you don't have to worry about it. Is it clear to everyone? Okay, just forget about it. Okay, basically what we have studied, this is the most popular and this is the most generally used pumping lemma. So just focus on it. So just focus on it and solve questions using it. Is this clear to everyone? In the GATE exam, they will not ask you question. They can ask you question. I don't know which question they can ask, but whatever is happening, this you can use. The pumping lemma that we have studied, in every book you will find this. Okay, whatever book you study, Ullmann, Sipser, Peter Lynch, whatever book you study, you will find this. In exercise, you will find the generalized pumping lemma. So don't confuse, just use this, what we have studied. So just focus on it and solve questions using it. This is enough. This pumping lemma is enough. This is what I'm saying. Or I can say by default, this is the pumping lemma basically. Any doubt? Any other doubt, Hari Krishna? Is your doubt clear? And you are asking for minimum pumping length. Let me tell you, these are slides from university. These are slides from a standard university. And in the standard, see, actually, if you see these slides, look at these slides. These are from a university. I have not created them. These are from a top foreign university. So they are also having minimum pumping length. You can see all these slides. This slide, they are asking minimum pumping length. Okay. In this slide, they are asking minimum pumping length. Okay. You can notice minimum pumping length. So this is from university. So I think this is a valid question. In the GATE exam, they can ask you this question, that what is the minimum pumping length? Is it clear? Yes, Vidyasagar, correct. Any other doubt, anyone? Did you understand pumping lemma? Like I tried to prove it. Why length of y cannot be 0? You tell me. That is a simple point. Can anyone tell me why length of y cannot be 0? Why length of y cannot be 0? Why we cannot take y as empty? In pumping lemma, why y is not empty? Because if you take y is empty, then every language will satisfy. Because if we allow y equal to empty, then every language will satisfy pumping lemma. Yes or no? Every language will satisfy pumping lemma. Every language, whatever language you take, every language, regular, non-regular, whatever